Okay, shall we get started? Cool. Let me reduce the. Is this better? Okay, maybe this is a bit better. I don't hear myself. A little bit more. I think it needs to go down to -20. Okay, that's better. That's the beauty of measurements. As long as they're consistent, you can set it and then it stays the same, right? But that's not true for retention times, as we discussed. It changes over time. Okay, so we're going to continue our exploration of data retention and memory refresh, and then finish that and talk about latency. You can see that the lectures are structured such that we talk about different scaling issues. One is we talked about reliability issues like RowHammer, it's a key one. Another reliability issue, data retention. And then we'll talk about latency, which is closely related to reliability, because you need to give some time to access things so that you can get reliable data readout from any memory. So these are all scaling issues with memory. But before I jump into that, I will announce a seminar, which is actually quite related to what we have discussed. This person, Dr. Sudhanva Gurumurthy from AMD, he's going to give a seminar on October 25th remotely. He'll be in Austin, Texas at 16. And he's going to talk about a 3D stack technology, HBM3. And he's going to talk about what kind of things are employed in this to make it much more reliable. So I recommend people to attend. Maybe we should have an assignment on this. What do you think? It's good for people to see these things. This is an industry perspective, clearly. And he has been at AMD for a while. Oh, you can read the abstract and the bio if you're interested, but he's basically going to explain HBM3 is expected to be widely used in future system on chips to accelerate data center and automotive workloads. Reliability, availability, and serviceability are key requirements in most of these computing domains and use cases, and essential for attaining sufficient resilience at scale. So he's going to talk about basically what kind of things that they have done to design the high bandwidth memory architecture. And AMD has played a big role in designing the specification as well as mechanisms in HBM3 architecture. So it should give you a good sense of what's going on in industry in terms of resilience. And you can ask questions also. So for example, I'm not sure if you will cover RowHammer and HBM. I'm very curious. I will ask that question if no one asks, but we'll see. So I would recommend people to attend, and there might be an assignment related to it also. And remember, we discussed the leaky DRAM cell. I like this picture because it does look like a DRAM cell. There's an access transistor over here, and then there's a capacitor over here. And then it gets leaking, right? And yeah, imagine billions of these leaking. Not good. And we talked about radar, a mechanism, and we were trying to make it real, right? Or make retention time profiling accurate in general. And we were discussing issues related to this, especially making radar work, right? Radar was the idea where someone determines the retention times of different DRAM cells, and then the memory controller refreshes different DRAM cells at different rates, at the rates they're supposed to be refreshed at. Of course, if someone determines the retention time of different DRAM cells accurately, you can use it for other purposes, as we have discussed. We may go back to that later on. But I think this is a good idea. But making ideas work is actually the tough thing, especially in a space like this. So let's talk about how to make it work. We were talking about profiling challenges, right? How do you identify the retention time of all DRAM rows? And feel free to ask questions, by the way. In person, it's much better. You can stop me at any point. So we were talking about DRAM retention time profiling, determining the retention time of every single cell in DRAM. The question was, is this really easy? And we said no. We talked about two phenomena that make it very difficult. One is data pattern dependence, or data dependence. And the other is variable retention time. Data pattern dependence is the fact that the retention time depends on the data stored in the cell, as well as cells around it, because of capacitive coupling that's induced between the bit lines as well as the word line and the bit line. You get this different charge leakage rates based on the data values, based on different capacitive coupling, essentially. And this makes it hard to profile because you need to figure out the worst case data pattern to figure out what's your worst case retention time. Or you could adapt the retention time to the data pattern, right? And that's a bit harder also, right? You can say, if I store this data pattern in this region, I'm going to refresh that region every n milliseconds. That's corresponding to that data pattern, right? You could potentially do that. You could potentially do optimizations like that, of course, but that's also not easy, clearly. You still need to understand the relationship between data pattern and retention times. And we also talked about variable retention time, and we said that this is the phenomenon that as you, basically the retention time of a DRAM cell is not constant. It changes because charge gets trapped in the access transistor gate. And when that charge gets trapped, leakage happens much faster from the capacitor. This is what's called trap-assisted gate-induced drain leakage. And this is a fundamental phenomenon in DRAM. As I mentioned, it was demonstrated as early as 1987 by Yeni et al. But we said that recently we have shown that this became much worse. Basically, this was considered to be not that bad in earlier DRAM generations, but our recent works have shown that this became much worse. So there are many cells that are exhibiting variable retention times. As a result, it became very difficult to do retention time testing. And this second one is one of the major reasons why DRAM manufacturers introduced in DRAM error correction codes. So you have DRAM, and previously you didn't have any error correction inside the DRAM chip. But more recently, DRAM manufacturers figured out that it was very difficult to identify cells that would essentially cause retention time issues because of the variable retention time problem. As a result, they said, we're going to protect all the cells with single error correcting codes. And that's the error correcting code that they added to the chips. This was mentioned in Samsung and Intel paper that we mentioned earlier. I'm going to go back to that paper later on. They basically say refresh and variable retention time are some of the biggest issues in DRAM scaling. Of course, they didn't talk about RowHammer in that paper, if you remember. I think they have a different opinion, but they may not be able to talk about it as openly, especially at that early at the time. Okay, any questions? Yes. Why does it happen? Well, why does it happen is essentially it's because of a charge trap. As far as we know, it's the circuit. There are noise issues in the circuit, right? You have this access transistor, and there are parts of the access transistor that are not perfect. There are parts that attract the charge and keep the charge. Basically, charge gets trapped in the access transistor because it's not perfect. And once charge gets trapped in that access transistor, incoming charge from the capacitor flows much faster. That's the problem. So this is you can always think about these as circuit level deficiencies. Yes. I mean, if you can measure it, yes, but the measurement is really done by the sense amplifier in a sense, right? But we cannot individually measure it because these are so small. We don't have measurement capability. Yeah, that's an interesting question. But internally, what happens, the sense amplifier kind of tries to do that, right? Yeah. We can model it, but modeling may not be perfect also. Modeling is not that easy as well. Okay, good questions. Okay. So these are the two major phenomena, and then we're going to try to solve them. Basically, we discussed the issues that this introduces. I mean, especially the second issue, variable retention time. You don't know the retention time until you figure out, until you test long enough. You need to test long enough to figure out whether the cell is vulnerable to variable retention time. And if the cell switches between two different states, let's say in one state, it can keep data for tens of seconds. In another state, it can keep data only for 16 milliseconds. You need to wait long enough to get to the state where the cell retains data for only 16 milliseconds. But again, this is a random process. You don't know when this will happen, right? So that's the tough part with variable retention time. And as a result, in general, variable retention time in this paper, we analyzed both phenomenon. I'm not going to go through all the results, but this is going to be a recommended paper you can read. In general, to identify variable retention time, you need some sort of error correction codes. You can reduce basically, you can reduce your refresh rate for a given cell. If an error happens, it could be because of variable retention time, assuming that you handle the data pattern dependence correctly. Okay, so that's what we're going to talk about a little bit. Let's talk about finding DRAM retention failure. So the question is basically, this paper shows that it's not easy, basically. Building something like Radar is not easy because we have data in the field showing that these issues are very difficult. The question is, can we overcome them? And then later research tackled to overcome them. Basically, this is the question to ask. How can we reliably find the retention time of all DRAM cells? If we can do that, we can make the DRAM more reliable and secure, hopefully, even with regular refresh rate, periodic refresh rate, or make techniques like forward-looking techniques like Radar work, or maybe some other techniques that take advantage of the retention time information. And that will improve performance and energy. So later, there's a lot of work actually that tackles this. I'm going to mention some of them. This is an experimental study that shows that variable retention time is actually really, really bad. I'm not going to talk about this. And it basically looks at different error mitigation techniques, including online profiling we discussed earlier. This, I think, proposed a good solution for variable retention time. I'm going to mention this a little bit. And the idea here is to once in a while profile the DRAM to figure out what is the retention time of the cells and adjust the refresh rate for each row, but do that in the presence of ECC. So error correction codes exist in DRAM. So each row, you can see that this is DRAM rows, and then each row is protected by error correction codes. And what you do is you have a refresh rate table. This is a per row bit vector. Unfortunately, we don't use Bloom filters over here for various reasons. But each row has something saying that should it be refreshed less or should it be refreshed more? So if you've identified errors in DRAM cells because you have reduced the refresh rate, you increase the refresh rate so that the row is refreshed more. Does that make sense? So the things where you have identified errors with ECC, you upgrade it essentially. That's the idea of upgrade. And once in a while, you still profile the retention time of the rows. And if the rows have low retention, high retention time, then you can basically downgrade the row, meaning change its refresh rate to a lower value so that it gets refreshed less. So it's a dynamic mechanism. It basically once in a while tests the retention time, decides which bin the row goes into, low refresh or high refresh. And if it gets errors in a low refresh bin, then you upgrade it to a high refresh bin. That's the idea. I'm not going to go through this in general, but essentially, for example, this shows that if you get an error, you upgrade the row so that it gets refreshed more often. And you can actually, here you have 2 refresh rates. You can generalize it to n refresh rates clearly, right? The hope is that this protects the row from future retention failure. So you have strong enough ECC over there. In this case, we employ single error correcting, double error detecting ECC. And it shows that this paper shows that you can mitigate variable retention time by increasing refresh rate when you get errors. And there's also memory scrubbing. Remember, you mentioned memory scrubbing. Once in a while, you check whether there are errors that had happened in your memory. This happens especially in server systems today. The memory controller scrubs memory. It basically checks the entire memory, sees if ECC has detected or corrected any error. And in that scrubbing, you can basically increase the, you can basically decide whether you want to increase or decrease the retention or the refresh rate of a row. There are algorithms in the paper you can look at. Okay. So what does this buy you? If you look at this, if you don't have any variable retention time, you get some refresh savings if you have 2 refresh rates, right? High versus low. And that is constant. If you have some variable retention time phenomenon that's happening over a year, you can see you tested the DRAM chip at time 0, and then you wait for a year. You don't do any testing. You have ECC, as we discussed, and you upgrade DRAM cells that experience errors based on ECC. Over time, the savings in refresh reduces, as you can see, right? Because there are some cells that experience VRT, variable retention time, over time, and they're refreshed frequently. They're not refreshed not frequently. As a result, you don't save as much in refresh, but you don't lose that much also. Now, Avatar is a reliable solution, whereas no VRT is clearly not realistic because we know that variable retention time exists, right? This is then ideal upper bound. And this is showing that even if you don't do the testing for 12 months, you can still gain 60% reduction in refreshes. So that's not a bad result. That's the idea. So once in a year, do this retention time testing, but you still need to do the scrubbing to make sure that errors are corrected. Okay, and there's more results in the paper that shows, again, comparing to no refresh, it gets about 2/3 of the benefits of ideally eliminating refresh, which is not bad. So it's still not good enough to eliminate all of the refreshes, as you can see. But we're using only 2 retention times, two refresh rates. I think it was 64 milliseconds and 512 milliseconds, if I remember correctly. But you should read the paper. And the benefits, as expected, are higher in larger DRAM chips, higher density DRAM chips. And there's also more analysis on energy delay products. This takes into account both energy as well as performance. As you can see, the lower is better in this case, and the energy delay product also reduces compared to 1.0, which is the refresh every 64 milliseconds. And it's reasonably close to no refresh, as you can see over here. Okay. And there's more in the paper if you're interested. So this paper, as far as I know, is the first paper that can enable heterogeneous rate refresh reliably. There are some reliability issues here that this paper doesn't tackle, but you can read other papers for that. But this is, I believe this is actually a good way of handling these random errors. Remember, we discussed using ECC for RowHammer errors, and we said that it's a bad idea in general because RowHammer, we know exactly what's happening. Here, in variable retention time, we have no idea what's happening, in the sense that we don't know which cell will experience variable retention time. So error correcting codes are a great way of handling those cells. And these error correcting codes can catch those cells where we don't have any idea which cell will be essentially losing its charge because of variable retention time. Yes, please. Mm-hmm. Yeah. Mm-hmm. Yeah, that's a very good question, basically. So what's a lot of these works proposes, they basically say the memory controller essentially issues an activate to do the refresh for a given row. It basically doesn't use the refresh command in general. Does that make sense? So basically, it's not bound by the refresh command's constraints. So you just issue if you figure out that a cell is going to lose its value, just issue an activate that serves as a refresh and then pre-charge theory. That's a very good question, though. How do you make it work with existing refresh commands, especially if you want to increase the refresh rate a lot? There are solutions to it, but let's not go into that right now. Yes. Yeah. Well, ECC works for RowHammer, assuming it's very strong, right? Because RowHammer induces bit flips in, let's say, 8 bits in an ECC word, and to protect that, you need 8 error correcting codes. Right? Does that make sense? Whereas variable retention time is a very random process. Normally, you get 1 bit. That's problematic, and if you have a single error correcting code, that corrects it. Yeah, that's the reason why ECC is very costly for RowHammer. Yes. So you're saying always use a low refresh rate, and then that ECC. Oh, the problem is errors may accumulate, right? If you always use a low refresh rate and you don't upgrade some of the rows, that row that's experiencing variable retention time may not be a good fit for low refresh rate. So it may get an error once, and then 10 months later, it may get another error. And then at that point, ECC may not be able to correct it. But I guess what you're saying is with scrubbing, you can fix it. That's true, but ECC also has overhead, right? So error correction also has overhead in general. So scrubbing, when you correct the errors, you don't want to be correcting too many errors, let's say. Upgrading the refresh rate so that you can refresh something more frequently reduces the load on the ECC. Does that make sense? Yeah. But that's a good question, I think. In fact, I think ECC and refresh are two ways of handling retention time problems, right? If you make your ECC strong enough, you will not have any retention problems. If you make a refresh rate strong enough, fast enough, you will not have any retention problems. These works are actually trading off between ECC and refresh in some way. Okay, so I'll move on. So there are other works that I'm not going to cover, but we have examined data-dependent failures a lot. This is a paper that talks about data-dependent failures and how to detect them. I'm not going to talk about that. This is a paper that takes advantage of data-dependent DRAM failures. For example, if you have not written to a row, you know that the refresh rate is not going to change due to data pattern dependence. As a result, change the refresh rate to a row only when you write to it. That's the idea. And this paper analyzed the write patterns of the programs to decide when to change the refresh rate based on data pattern dependence. I will mention this one a little bit because this is actually a work that handles both data pattern dependence and variable retention time. And I'll just give you the basic idea. So yeah, I think we already discussed this. Basically these retention times are hard to identify. We talked about variable retention time, data pattern dependence, but there's also other stuff like voltage, temperature, process non-idealities. These things, especially voltage, is a bit tough over here that we didn't really talk about. That's why online profiling actually makes sense, because there may be some errors you may be missing, even if you handle variable retention time and data pattern dependence perfectly, let's say, because there may be voltage fluctuations, power supply fluctuations. These may not happen very often, but these affect your reliability and retention time actually. But anyway, I just want to mention that that's not perfectly relevant to what we're going to discuss. But basically, ideally, we would like to quickly and efficiently identify error-prone cells that will fail at a given retention time. So this work is the first study that looks at real low-power DRAM chips, and it identifies data retention characteristics. And I mean, this is obvious clearly, but it observes, again, that cells are more likely to fail at a higher refresh interval or higher temperature. And we have discussed this, and other papers have shown this. And profiling is actually a complex trade-off space. Online profiling for retention time is a complex trade-off space. How fast you can do, whether you can cover all the cells that are going to fail at a particular retention time, that's called coverage, and what kind of false positives you get. False positive in this case means that you think a cell is going to fail at a given retention time, but it's not going to fail actually. So you're too aggressive in refreshing that cell, even though that cell can retain data much longer. So these all impact the benefits. So coverage is important because ideally you want to get 100% coverage of failing cells at a given retention time, because if you miss some of the failing cells, you will get errors, right? Well, you can rely on ECC, of course, right? ECC always helps you for those missing cells. But if your coverage is too low, then your ECC needs to be even stronger. So this is a complex trade-off space, and this paper is the first paper to explore that trade-off space. It's actually not an easy trade-off space, as this paper shows, but I'm not going to talk about that. But the idea this paper introduces is actually a nice one, I think. Basically, the idea is this. If you want to operate at a particular refresh interval and a particular temperature, if you want to identify the cells that are going to fail over here, profile at more aggressive conditions, meaning profile at a higher refresh interval and higher temperature so that you can operate here. So whatever you find over here is let's say, superset of the cells that are going to fail if you operate over here. That's the idea. The question is, of course, what is that here? What are the exact values? And the paper does a study of that, which I'm not going to go into. So what this does is this makes the profiling faster. It's more reliable because you can more quickly figure out the errors that happen compared to a lower refresh interval over here. But false positives are possible because what you find out over here as failing cells are a superset of the failing cells that are under these operating conditions. But it's a very intuitive idea if you look at this picture, hopefully, right? Does it make sense? Yeah, okay. Yeah, but then the question is, of course, how do you explore the space? Because there's a huge space, right? If you want to operate here, let's say at 50 degrees Celsius and at a refresh interval of 32 milliseconds, where do you really profile? And that's what the paper does with experimental study of real DRAM chips, which I'm not going to talk about. But if you actually design a profiling mechanism based on this idea, you can get much faster than state-of-the-art baseline profiling mechanisms that usually cover essentially, that usually do a lot of rigorous testing of the entire memory. And you get close enough to 100% coverage, as you can see, but at the expense of 50% false positives. So you lose some benefits of heterogeneous rate refresh because now you have some false positives. You can change the trade-off a little bit. You can make this even faster with more false positives without affecting the coverage that much. So that's the trade-off space. And this clearly affects the overhead of online profiling, because whenever you do online profiling of DRAM, there's some overhead, right? For example, right? If this was doing some online profiling, there would be some overhead of accessing DRAM in terms of energy as well as potentially performance if programs were running. So faster is usually better. If you lose coverage, there's overhead on ECC. If you have false positives, you're missing opportunity because you're not able to reduce refresh for some cells that are actually quite strong. So I find this fascinating. And there needs to be more work in this area, frankly. This is the state of the art in, even in 2022, this is the state of the art in online profiling, in my opinion. This is 2017. This paper was published in 2017. But we're going to talk about some things that consider error correcting codes. And this paper also shows that by doing this sort of profiling, you can enable longer refresh intervals by reducing the overall profiling overhead. And it shows significant performance improvement and power reduction. You can read the paper for more detail. And that's the paper. Any questions? Yes. Faster means so profiling is a process, right? It takes time to test every single DRAM row. For example, if it takes 10 seconds, I just made it up, 2.5x faster will reduce it to 4 seconds. No, basically you test and figure out which cells you should refresh at what rate. Yeah. No, 2.5x faster means that the testing to identify all cells that are going to fail at a particular refresh rate, the testing to identify the retention time of all cells is 2.5x faster. That's the speed of testing, basically. That's not the speed of program execution in the end. Yeah. Okay. Because if you think about like a brute force testing method, like we discussed earlier, you have to check whether a cells retain data at different refresh intervals. So assume that you want to look at 2 refresh intervals, 64 milliseconds and 512 milliseconds. You have to test every single DRAM row at those 2 conditions, 64 and 512, and the temperature, of course, if you want to change the temperature, and figure out whether a row has errors in either of those conditions. So that's basically looking at every single DRAM row. This is reducing that by basically testing at higher temperatures and higher refresh intervals only. Make sense? Yeah. And higher temperature testing actually reduces increases the leakage, so that actually makes the testing faster as well. Yes. You had a question? Or? Okay. Okay, so I'll move on unless there are questions. So, okay, all of this is without in DRAM ECC. Now it turns out if someone adds error correcting codes inside the DRAM chip, it complicates all of this testing because error correcting codes interfere with what's going on. So this actually makes life much harder. So far we were assuming error correcting codes are outside the DRAM chip. You figure out your retention times and then correct the errors. But if someone basically somehow corrects the errors, what you see on the memory controller side is the corrected bits essentially. And if that error correction code is not able to correct the errors, what you see is a garbled word. So it may not be actually what you really want. So basically in DRAM error correcting codes complicates things. And I'm going to give you one example of this. So this is Minesh's work. He did a lot of work on this in his PhD. Actually, I'm covering all of his major papers that went into his PhD. This one's the first one, second one, third one. And this is the fourth one. I'm going to talk about the fourth one. I will talk about the first one. But basically, what's the problem? So you have some memory over here, and you have a profiler that tries to figure out the retention time of the DRAM cells, right? But memory itself has some on-die error correcting code mechanisms that you don't know about. The goal of the profile is to figure out under a given condition which bits are likely to fail, meaning lose their data. And the problem is this on-die error correcting code on the DRAM chip changes how errors appear to the profile. Let's take a look at why. So basically, I'm not going to give you all the results, but this on-die ECC transforms the bits. So it can correct if there's no error, for example, it doesn't do anything, of course. But if there's some error in a word, in a data word, it corrects it. If it corrects it and without problem, then the profiler is not aware of the fact that an error happened, right? But basically, it's hiding the fact that some error happened. So profiler is losing some information. That's one reason why the profiler doesn't have complete knowledge right now. So it's better to put the profiler over here, you would argue. Yes, I agree. So that's good. So this is one problem. Profiler doesn't have correct information because it's expecting something. It's expecting errors, but it's not getting errors, depending on the strength of the on-die ECC. What is really worse is this on-die ECC, when it's not able to correct the errors, it actually introduces other errors inside the data word because of the way ECC operates. That's the way usually now error correcting codes operate. They basically take a word, they try to correct the errors, and if they're not able to correct the errors, they output some word that may have lots of errors, actually, lots more errors than what really happened over here. So it's really transforming the bits into something that the profile cannot make sense of. That's the idea. Makes sense, right? Yeah. So it has redundancy. It basically, you can think of this as you have the data, and then you have the code. And the data value is represented with the code redundantly. If a data value, if a bit over here changes, then you can detect that with the code. And then you, depending on the strength of your code, you can figure out which bit changed. But if there are too many errors over here, then the code was designed to correct, then the code is not going to be able to correct the errors. When it's trying to do this transformation, it's going to basically output something that's garbled. Of course, you can fix the problem, and this paper proposes how to fix the problem, which is a relatively easy thing, actually. So basically, this is the problem. On-die ECC actually increases. This is proven by experimental data in these works. The total number of bits that you think are failing makes it harder to identify which bits are failing. And also it interferes with commonly used data patterns for memory testing. Because if you use some data pattern for testing, now you're assuming that data pattern is the worst case data pattern, for example. But on-die ECC, given on-die ECC, that may not be the worst case data pattern, basically. So you don't have this information, essentially. So essentially, this work identifies that there are two sources of errors. So this is, let's say, the word, and then it goes through ECC decoding, and there's an error over here. If the ECC cannot correct the error, it adds another error. Basically, this is as simple. So there's a direct error that happens actually in the data word due to errors in the memory chip. And there's an indirect error, which is an artifact of the on-die ECC algorithm. The key idea in this work is to separate them and expose them to the profiler. Okay. Yeah, basically this decoupler profiling for direct and indirect errors. And essentially, there are two profiles in this case. One is the active profiler, which identifies all direct errors. So data store is provided directly to the active profiler without going through the transformation of the on-die ECC. There's a bypass path. Other works also propose that. And I believe in future DRAM, there's going to be something like this. And there's a reactive profiler, which identifies the indirect errors. And there's a secondary error correcting code in the memory controller that tries to, well, it doesn't necessarily try to correct them, but tries to identify them. Yes. Yeah, so that's a great question. Cost, let's say. So there's more cost on the memory chip, right? I believe it's doable with some support, additional support inside the DRAM chip, but it may take time. And also, I think cost is one issue. The other is the DRAM standards. So we're going back to the DRAM standard. It's a very rigid standard. DRAM has, as we discussed in an early last lecture, actually, there's no breathing room for DRAM, right? DRAM itself cannot do anything internally because it takes time. So if you implement something like we discussed in an earlier lecture yesterday, self-managing DRAM, it becomes easier to do online profiling inside the DRAM chip. Today, there's no way you can do it inside the DRAM chip, even if someone paid the cost over there, because you need to change the DRAM interface as well. Very good question. Any other questions? We're getting very good questions, so keep them coming. Okay, and this is, that's it basically. I mean, there are some, essentially you're reducing the problem of profiling with on-die ECC to profiling without on-die ECC by providing this bypass path, and also having the secondary ECC to identify the other errors. So this shows, maybe I'll not go into the results, but essentially it's a faster algorithm again, compared to baseline profiling algorithms. And also it outperforms the best performing baseline when you try to mitigate data retention errors, like we have been doing earlier. But I will not go into the details of the evaluations. You need to read the paper. So these are actually quite sophisticated evaluations in the end. And if you're interested, I'd recommend looking into this. So DRAM manufacturers, I think going forward, are going to provide something similar, but don't count on me. Maybe Ataberk knows better. Do you know? This is a good question to ask also for Sudanwa when he covers his talk. What are you doing about NDRAM ECC in HBM? Yeah. I mean, the issue is, this is actually a bigger issue. Even if you have, even if you don't do profiling, if you want to have some system level ECC on the memory controller, if DRAM is correcting some errors internally and it's giving you garbled data, the system level ECC that you have in the memory controller has a bigger problem basically, because it's trying to now it's going to try to correct errors that are much bigger than what it really expects. So having this internal in DRAM ECC is actually very dangerous without providing information about what's going on inside the data store. And that's what we argue in our transparent reliability paper also. No, you have comments? Okay, no comments. By the way, we should really pass the microphone because I'm not sure if people online are hearing the questions. Do you have the microphone with you? Yeah, like when people ask, I don't know. Maybe you can exploit locality or something. Okay, okay, and that's HARP. And you can actually experiment with it because all of this is open source. Okay, so now let's, this was profiling, right? Yeah, and you can see that profiling is hard. There's still more work to do in this area, as I mentioned. But let's talk about binning, which is the second part that you need in a mechanism like Radar. And the idea here is to store the rows into bins by retention time. And I mentioned that we're going to use Bloom filters, and I didn't discuss Bloom filters in a lot of detail. We're going to go into a little bit more detail. So how many people know about Bloom filters now? Okay, now that you've learned, how many people do not know about Bloom filters? Enough, let's say. I gave you the basic idea. Okay, so let's go into it a little bit more. So basically, the idea here is how to efficiently and scalably store rows into retention time bins. So essentially, retention time bins are, you can think of this as sets, right? You're representing the set of rows that need to be refreshed at a certain rate. And you have multiple sets. Set of rows that need to be refreshed every 64 milliseconds, another set of rows that need to be refreshed every 128 milliseconds, and the remaining set of rows that you don't need to represent, assuming you represented the other two correctly, right? And the idea is to use hardware Bloom filters. As I mentioned, Bloom filters was proposed by this paper, which I'm going to show you later. And the idea of a Bloom filter is it's a data structure. It could be implemented in software or hardware. Any data structure can be implemented in software or hardware, depends on efficiency, right? Actually, anything that you do in software can be done in hardware. It really depends on how efficient it is in the end. It's good to have this mindset, I think. That way you can actually change a lot of things in your mind. But basically, Bloom filters can be represented very efficiently in hardware. But it's a data structure that probabilistically represents set membership. What does this mean? Presence or absence of an element in a set. And it does approximate set membership. So if you think about non-approximate set membership, you need to be perfectly correct, right? Here, you don't need, you relax the requirements. You don't need to be perfectly correct. Relaxing the requirements makes this data structure unusable, some problems that do not satisfy those properties. We will see that. But for example, non-approximate set membership. What does this mean? If you if you have n elements in the space, n possible elements in the set, use one bit per element to indicate whether whether each element is absent or present in the set. I think of this as, let's see if this works. No, good, something is working. I think of this as a bit vector, right? Basically, let's say you have, I don't know, I'll make it up, 8 billion rows. You have 8 billion rows in DRAM. Each of them has a bit associated with it, and you set and you want to represent two membership in the set where the rows need to be refreshed every 512 milliseconds. I'm just making it up. And you set the bit to 1 if the row needs to be refreshed every 512 milliseconds. I guess 1 means refresh every 512 milliseconds, and 0 means refresh every 64 milliseconds, right? That's the idea. So basically, you have a bunch of rows that are 1s or 0s. But now you have 8 million bits. And retention time profiling enables you to figure out whether a row is 1 or 0, right? So the problem with this is it's a lot of hardware overhead to store 1 bit. And it's a very sparse data structure, potentially, right? A lot of the bits may be 1s or 0s. So what Bloom filter does is, it really does, okay, I don't know if you can see that now. Oh, okay, that's better. Approximate set membership. Basically, you use a much smaller number of bits. That's it. I don't know, 1K, let's say. Now you reduced 8 billion to 1K. 8 billion was an exaggeration, but fine. It's still possible if you have a huge chip, right? Yeah. And then you use a much smaller number of bits and indicate each element's absence or presence with a subset of those bits. Maybe subset could be 1, right? But what do you do right now? Here, each address, this is row 0, right? There's a direct correspondence between row address and each bit until you go to row 8 billion, right? Here, you don't have that nice correspondence anymore. You have a row address. You don't know which bit it corresponds to. Well, because there's no direct correspondence. You need to make it correspond to some bits. So what do? Well, I guess I'll do it this way. You hash the address bit somehow and determine which bit a row maps to over here. There's some hash function, basically, and people have developed hash functions so that you can minimize the false positives over here. So this hash function enables you to take a row address and map it to a bit. And then, for example, you determine that row address 5 needs to be set to 1, meaning it can be refreshed every 512 milliseconds. Assuming that hash function gets you to this bit, that bit is set to 1. Makes sense, right? Now you populate this much smaller data structure, 1K, with the bits that are going to be set to 1. So let's say your row address also, I don't know, that was 5. That was, let's say 25 is set to 1. That maps to somewhere here, you set that to 1. And let's say your row address, I don't know, 5 billion is set to 1. Let's assume that it maps to the same place row address 5 maps to. In this case, it's fine, right? Because you're trying to, both of these need to be refreshed every 512 milliseconds. So you're setting both of them to 1. The bit was already set to 1. It's perfectly fine. There's some aliasing. Basically, there's some aliasing that happens because you don't have enough bits to represent every single row. But this aliasing is an okay, there's okay aliasing because this bit was set to 1 and it should have been set to 1 for this row also. But what happens if you have a row address, let's say, I don't know, I'll make it up again, 5K. Oh, did I already insert 5K? Don't worry about it. I shouldn't use 5 too much. 12K. That's the row address. Let's assume that also it happens to map to also here, but we don't want to insert it. It's really 64 milliseconds. Now you have a problem, right? So this Bloom filter doesn't work. Do you agree? So basically, you have inserted, you have set the bits saying that this row should be refreshed every 512 milliseconds. And you want a row address that should not be refreshed every 512 milliseconds gets mapped to that location. Right? So what did I do wrong? Basically, I should have represented. This is actually an aliasing that's very bad. You don't want this to happen. So this is a bad Bloom filter design because the Bloom filter doesn't satisfy your property, right? You don't want to have an address that should be refreshed every 64 milliseconds to be aliasing with something that should be refreshed every 512 milliseconds, right? So this is bad use of a Bloom filter. And I wanted to demonstrate that because this is not how you would design the Bloom filter for this problem. How you would design the Bloom filter for this problem is basically represent the set of rows that need to be refreshed every 64 milliseconds. That's it. And then if anything is not present in that Bloom filter, that should be refreshed every 512 milliseconds. Make sense? Okay, so that's how you can convert the problem into a Bloom filter type of problem, right? Okay, so this doesn't work. Hopefully it's clear to everyone why this doesn't work, right? Because a row that should be refreshed, that should not be refreshed every 512 milliseconds, that should be refreshed 64 milliseconds, was represented as if it should be refreshed every 512 milliseconds because its Bloom filter entry aliased with some other row that should be refreshed every 512 milliseconds because of the bad Bloom filter design, right? This is not how we would design the Bloom filter. How we would design the Bloom filter is actually much easier, I would say. I don't know how to turn this off, but can you still see it? Okay, so a good Bloom filter would be you insert only row addresses that should be refreshed every 64 milliseconds. So this is a set of rows. Basically, it's representing the set of rows that should be refreshed every 64 milliseconds. Fast refresh, essentially. I should call it fast refresh. Now, what happens is we're going to add row 12K over here. It's 1. Now, assuming that everything else in the design remains the same, you still go through the same hash function, same size, etc. Now, the other rows that aliased over here, I think we said 5 billion, right? Row 5 billion would alias. You would think it should be refreshed every 64 milliseconds. You're wrong, but it's okay, right? Because that row, you're going to refresh it as fast as possible. Yes, you're going to lose some opportunity because that row doesn't require refresh every 64 milliseconds. It can basically tolerate refresh every 512 milliseconds, but you're not going to be wrong. You're not going to lose data, right? So this is called a false positive over here. But it's an okay false positive over here. So most of them are false positive from the perspective of the Bloom filter, but this is a very bad false positive because of the design of the Bloom filter. So in this particular case, you can tolerate that false positive because of the way the problem is structured. Okay, that's the idea basically. That way, this way you can actually have a very small Bloom filter to represent the small set of rows that should be refreshed very frequently. And everything else gets refreshed less frequently, assuming 2 refresh rates. If you want to do another refresh rate, let's say you have a set of rows that need to be refreshed every 64 milliseconds, another set of rows that should be refreshed every 512 milliseconds, you probably need a bigger Bloom filter for this one because there are more rows here in that set. And then everything else may be refreshed every, I don't know, 1024 milliseconds or something like that, right? You need to decide, of course, those things. Okay. Yes. Yeah. So that's a great question, basically. That's a matter of sizing the Bloom filter at this point. Normally, because remember the curve that we had yesterday, because of that curve, you can make the Bloom filter smaller. So remember the retention. Okay. Oh, this is going high. Okay. Now I can play tricks. So remember the retention time curve that we showed based on data. This is 64 milliseconds. This is, I don't know, 512 milliseconds. So the number of cells that are failing over here was only 30 in a 30 gigabyte. So that number was very low. So you will insert only 30 things over there in a 32 gigabyte thing. That's why you can make the Bloom filter small. And this curve looks like this, if you remember. Okay, you're taking advantage of basically the distribution of retention times. But that's a very good question. If that number is much higher, if it's not 30, like if it's 1,000, then a lot of things will become 1 over here. So you'll get a lot of positives, false positives. And at some point, you should not get too much false positives because you lose opportunity. So you need to size your Bloom filters. You need to also fix your hash functions so that the distribution is also nice, right? Yeah, but Bloom filter design is actually a very heavily studied topic. Okay, so I'm going to go down and we'll continue. I think I've covered a lot of these slides over here, so let's go. Yeah, basically, as I showed you, some elements map to the bits, other elements also map to. And there are multiple operations on Bloom filters: insert, test, and remove all elements. So this basically generalizes what I showed you to 3 hash functions. Why do you want to have more than 1 hash function? Ever? Like, what is the utility of? I showed you something with only 1 hash function, right over here. You take the row address, you have 1 hash function, and it maps to only 1 bit. Basically, you still use 1 bit to represent a given row address. Here, if you have 3 hash functions, you're using 3 bits to represent 1 row address. Yes. Exactly. Yeah, to avoid collisions or aliasing, essentially. Because if you represent each address with more than 1 bit, the probability that 2 addresses will actually alias is reduced. Because let's take a look, actually. I have an example over here, so it's good to go through the example. So here, this is the set of rows that need to be refreshed every 64 milliseconds. And you insert row 1. You go through 3 different hash functions. These are basically doing different transformations to the bits in the row. And you set 3 different bits. That's what happens. And then this is how you test. This is the testing. Check row 1 is present. You go through the same hash functions. If all of the bits are set, that means that row 1 is present. You just inserted row 1, so row 1 hopefully is present. And then if you didn't insert row 2, let's check if row 2 is present. You go through the same hash functions. One of them is 1. One of the bits is 1. The remaining bits are 0. So you check if all of them are 1. Not all of them are 1. So you get a 0. That means that row 2 was not inserted, which is correct. Let's insert row 4. Inserting row 4 sets this bit, and this bit. They happen to be 3 different other bits, which is fine. Now we've inserted row 1 and row 4. Let's test if row 5 is present. In this case, row 5 is present, right? So you get a false positive. Now, I guess I don't have that example that I claim to have, but basically, if there was one other row, so this what should I say? Basically, the false positives now require all bits that you map to be set. Right? If you represent a particular address with more bits, the likelihood that you will get all bits to be set is lower. Now, this depends on how you design your hash function, of course. If you have a terrible hash function, this may not be correct, always. But if you design your hash function well, the probability of collision actually reduces. Does that make sense? And also, it also depends on how many things you're inserting. If all of these are 1, clearly what I said is not true, right? So in the extreme cases, in bad cases, this may not be true. But in the general case, you will get fewer collisions because you require a stronger test for set membership or set presence in the set. And that stronger test tests more bits. Of course, the downside of more hash functions, you're doing more computation, right? Okay, so this is the paper, and I recommend people to read it. It's an old paper. As you can see, it was written in 1970, but it has a lot of impact in computer systems. You can use Bloom filters to represent anything in software also, any kind of set membership where your problem works with this. Let me see. Yeah, I will not read it. So you can take a look at it. Okay, so let's talk about advantages. Clearly, this is storage efficient representation of set membership. Inserting and testing for set membership are fast. These are 2 very fast operations. No false negatives, meaning if you insert it, if Bloom filter says an element is not present in the set, the element must not have been inserted. This is correct. Basically, it gives you no false negatives, basically. But well, disadvantages false positives. We'll get to that. But it enables trade-offs between time, storage efficiency, and false positive rate by sizing the Bloom filter and using the hashing functions in terms of both the function itself and the number of hashing functions. The disadvantages, of course, are false positives, as we discussed. An element may be deemed to be present in the set represented by the Bloom filter, but it may never have been inserted, as we have seen. You have to be able to tolerate these false positives in your problem for you to be able to use Bloom filters, or you need to transform your problem so that it can tolerate these false positives. And as we have seen, using Bloom filters to represent fast refresh rate rows is able to tolerate this. But when you cannot tolerate this, it's not the right data structure, clearly. So I think we've already said this basically. We can tolerate false positives if you use refresh rate bins, because a row may be declared present in the Bloom filter, even if it was never inserted. But it's not a problem, because assuming that you represent your problem such that you can refresh more rows, some rows more frequently than needed. You don't want to get into the situation where you're refreshing a row less frequently than needed. No false negatives, rows are never refreshed less frequently than needed. And it's scalable. So this is actually important also in a Bloom filter. A Bloom filter never overflows, unlike a fixed size table. So why is this important? Because another way of representing, well, where is this? Okay, there it is. Another way of representing this is not just using a bit vector, but using row addresses, using content addressable memory. Yeah, well, I don't know. Let's assume that you figure out that 100 or 128 entry table, right? This 128 entry table stores the row addresses that need to be refreshed every 64 milliseconds. 128 entries. And then maybe a valid bit also, saying that there's some row address that's stored there, because you may store something less than 128 entries, right? And then you basically figure out row 5, row 1K, row 5K, row 5 billion, ... All of those are valid. And what you do is, when you get a row address, you do a content addressable search. You basically check every single entry, right? Whether each entry matches the row address. If it matches, if a row address, if a given row address n matches any of the entries, any of the valid entries in this table, you know that it needs to be refreshed every 64 milliseconds, right? So it's a fixed size table. That's another way of representing it. This is actually a much more compact representation than this one, assuming the number of elements that you need to insert here is much smaller, right? And that's what we know, that that's the case based on that distribution over here. Now, this is nice, clearly. This is a content addressable memory, CAM, whereas this is clearly random access memory, RAM, right? If you think about it. The downside of this is clearly all of these comparators, etc. There's hardware cost, but there's another downside over here, which is scalability. Let's assume that you're doing online profiling, and you figure out that you need a 129th entry. Unfortunately, you don't have space for it, right? In this case, that's the problem with a fixed size table. Well, a particular fixed size table. It's not a problem with the bit vector, because you always have an entry for any row over here. It is not a problem over here also, because you just set some more bits, right? You'll get more positives, fine, but you will be able to represent the set membership of the new thing that you have figured out. So this sort of table may be a compact representation, but it's a very rigid representation, whereas Bloom filters are much more, let's say, scalable and non-rigid, flexible representation. Yes.
You mentioned that it's storage, like a wiring cost and computational cost in computing the hash function. I mean, is it easy to implement a hash function that is good enough with minimal wiring costs? And
yeah, it's usually not that bad. And you can read the paper, and the papers, like Wader paper covers it, but other papers also cover it. Usually those hash functions are not that bad. Usually they're shifting XORs, and usually they're not operating on very huge, like if you think about an address, it's 32 or 64 bits, right? It's not like 8,000 bits. So the operations are not that costly. Yes, it's not as simple as this one, clearly, but yeah, yes. Mm-hmm. I see. Yeah, yeah. That's a good question. Basically, if you had knowledge of which rows to discover, which rows are going to be that way, can you design a better hash function? I don't know. I think usually, I mean, potentially, depending on the row addresses, etc. But you can also change the row addresses potentially, right? If you know that information. Yeah. I think that's hard to do. Yeah, hard to do because then you need some reconfigurable logic, right, in the memory controller. Yeah, I think it's a good thought. In general, it may lead to a more flexible system, but I believe it's hard to do. I like your thinking. Maybe it's useful in some other context. Okay, well, Tabark is looking as if he has some comment. Okay, he's seen this many times. That's why he's basically going to come up with a new way of doing this now. Yeah, which is essentially the beauty of this stuff, right? You can always come up with a better way of doing things than the past. Okay, so basically, in the end, it's efficient. You already came up with some way, I guess. There's no need to store info on a per row basis, and it's simple hardware. And you can see the paper for more detail. The paper actually explores the space. Okay, so I think in general, use of Bloom filters in hardware and software are very good, actually. I would recommend you to think about this. We have used in our research, these are examples from some of our research. We have seen this in RowHammer, but we have used it in, for example, this work, evicted address filter. Here, Vivek used this as a representation of the addresses that were recently evicted from the cache. So basically, you can keep track of the addresses that were recently evicted from the cache. And if you need to access one of those addresses, the processor checks whether it hits the Bloom filter, which is called the evicted address filter. This gives an indication of what's happening in your cache. You just recently evicted the address from your cache, and the processor is going to access it, is accessing it now. Maybe you should change something you do in your cache so that you can capture these addresses better in your cache. And that's the idea in this work. So I believe there are a lot of other use cases of Bloom filters. Yes? You need a moving microphone or flying microphone. That's
I still have a question about the Bloom filters for leaky cells.
The what itself?
The leaky cells detect the cells that should be recharged as often.
Sure.
When would be the best? When should we clear the Bloom filter?
Oh, for leaky cells, that's a good question. Yeah, Bloom filter complicates some things, right? Clearing is tough. You cannot individually remove an element from a Bloom filter because of the false positives, collisions. So in general, we don't, for example, the radar work doesn't propose removing anything. You just keep accumulating things. So if variable retention time, if you're doing online profiling and having variable retention time, you keep accumulating things.
But if you keep accumulating things, at some point we'll be refreshing every cell.
Hopefully not every cell. The hope is that not every cell will hopefully be exhibiting variable retention time. But yes, we're going back to the avatar, basically. That's the reason why we didn't use Bloom filters in the avatar work. We use really single set membership, single bit per row. But I don't think it's scalable. So there needs to be some, basically there needs to be some idea to make it work well. And we don't know how to solve that problem yet. You're basically pointing a problem that I don't think anyone has solved yet. Make sense? Yeah. Okay. I mean, we have seen also Bloom filters and RowHammer. You can read that paper, but that's a different sort of Bloom filter because it's really a counting Bloom filter. As opposed to having single bit, it basically has a counter to detect things, to detect essentially access counts. Okay. Okay, good. So the last step in Radar is refreshing. I'm not going to spend much time on this because I think this is kind of obvious. Here, basically, you need to check the Bloom filters. Memory controller, every 64 milliseconds, memory controller generates some addresses to refresh and checks whether the row is in the 64 millisecond bin. If it's there, then it refreshes the row. And this gives you an idea of the size of the bin, 256 bytes, I believe. And this is 1 kilobyte over here. If it's not in the 64 millisecond bin, the memory controller checks whether the row is in the second Bloom filter. Then it refreshes the row every other 64 millisecond window. Otherwise, it refreshes the row every fourth millisecond, 64 millisecond window. So there's a way of implementing this, but this is not that interesting, let's say. And you can do it. Let's take a look at the Radar design. Like, where do you put Radar? In the paper, originally we suggested well, in the baseline, refresh control is in the memory controller, as we discussed. But radar can be implemented in either the controller or DRAM. If you do it in the controller, essentially the Bloom filters are in the controller, and the overhead is like this, and you can read the paper. But you could also do it inside the DRAM chip, and this is what the self-managing DRAM actually does it right, in my opinion. We just suggested that you could do it. Here, then you need, you still have some overhead. So downside is the overhead over here. But I think if you read the self-managing DRAM work, that's a good way of doing radar inside the DRAM chip. Okay, we already discussed this yesterday, so the benefits are high. Maybe we can do some brainstorming right now. So what else can you do to reduce the impact of refresh? We talked about getting rid of refreshes. So we talked about some ways of getting rid of refreshes. Maybe there are other ways of getting rid of refreshes, right? Maybe I'll just show this. I think we discussed this, but maybe there are ideas. Thoughts? Anybody has a huge idea? How long? We don't know. Yeah, I mean, some workloads may tolerate errors, right, as we discussed last time, and we're going to discuss a little bit more in the next lecture. Not refreshing may help. That's true, yeah. So yeah, if you're lucky, let's say. Yeah, I should have put that work over here also, yeah. So you can, if you can somehow ensure that your program's access patterns refresh all the rows that you need, then you don't need to have separate refreshes, right? That's the idea that Ataberk has mentioned. And I think I like that thinking. It's very difficult to do, I think, in the general case. We have a paper related to it. Hassan is a co-author. I should mention that. We should put that up over there. Maybe you can put it on Zoom and I can click on it. That's easier. That saves me some time to waste. Basically, refresh is the same thing as an access, right? If your program accesses a row, and if you keep accessing the row, let's say every 64 milliseconds, you don't need to refresh that row, right? That's the idea. If you can morph your program such that all of the memory that you need is always accessed every 64 milliseconds, that's great. How do you ensure that is a different question, of course, right? But I like this idea because it's a very clever idea to get rid of refreshes. Yes?
Is there a way, maybe the question is stupid, but is there a way like to do some block refresh, some batch refresh, several refresh at the same time, even though you don't need some, you would like find a way to do it in batches and so you would make it faster in the end.
So what happens in real DRAM is actually it happens that way. So what happens today is the memory control issues a refresh command. I don't know if you completely reverse engineered it, but about 8 rows get refreshed. Some number of n rows get refreshed internally. So there's some batching that's already happening inside the DRAM chip. And there are some proposals that we have that I'm going to mention that overlap the refreshes and accesses. Yeah. Yeah, if you want to do it even more, then it requires more effort. Yes.
And mention about introducing accessing, then I would think just directly to RowHammer, like if accessing it more than the refresh, then you will introduce errors.
Yeah. So RowHammer becomes a problem, yes, if you get rid of refresh completely.
So I would say
solve that in some other way, perhaps.
Yeah, I would say like the whole problem of this, the whole block of refreshing RowHammer are the arrows, are the flip bit of the arrows. So maybe we should look at the ECC, or we should look at the Bloom filter to actually know like which row is wrong, is getting wrong, and looking at which row is getting wrong, we refresh there. So, you know, the rate or the accessing to instead of fresh, those are the outside problem. The real problem is the which row is getting wrong.
Mm-hmm.
So maybe we should look at there.
I see. Yeah, basically you're suggesting have some sort of ECC to detect which rows are having problems and maybe add them to Bloom filters
Yeah, I
then-
think these two should link together, and the Bloom filter could introduce a higher refresh rate, or maybe it's not refresh rate. It's just when it's wrong, you refresh it.
Mhm.
I don't know. That's how I think.
Yeah, maybe. The downside, I think, is ECC needs to be very strong in that case. I agree, ECC can correct a lot of the errors, but in general, if you want to correct all the errors, your ECC needs to become very strong.
Okay.
Yeah, you're back to that problem, unfortunately.
Yeah.
Yes.
When we have a low memory usage, and we for the locality of data, like for local, you see the row, and so we don't have.
I see. Yeah. So you're trying to basically allocate a lot of data in the same row as much as possible so that you get more access to that, and you basically increase the refresh, like natural refresh that's happening because of accesses. Yeah. Yeah, I think once you think differently, you can design software methods like that to enable the no more natural refresh. Did you send it? Okay, maybe I'll point that work since it was not. Okay, it's in the chat. Yeah, if I click this, yeah, you can find it over here. It was published a couple of years ago. It was specifically for neural network accelerators because you know the access patterns and neural network accelerators much more easily. And that's the idea, basically. I just gave you the idea. It's called refresh triggered computation. You basically go through memory, and while you're going through memory, you actually do the computation also. So you're using the refreshes for computation. Or read another way, you just change your access pattern so that your access pattern always refreshes memory. That's the idea. You can view it that way, both ways, I think. We called it refresh triggered computation, but you can take a look at it. I think in the paper we show that some other applications also benefit, but I'm not going to go into that. I think this requires your application to be, let's say, amenable to this. It's very hard to do with a very irregular application, I think. Okay. Okay. Any other thoughts? Ah, that was not what I wanted. Okay, and I'll move on. Then feel free to add more ideas. And in your reviews also, whenever you do the paper reviews, I would recommend thinking about or adding more ideas. These are hard problems. So I have a lot of recommended readings, but this is one of them. Okay, we're almost at the end of this part, but I'll give you some more ideas also. DRM refresh is actually a critical challenge. As we see in real systems, refresh rates are increasing. And this is actually another good question to ask in a high bandwidth memory talk on Tuesday. Maybe Ataberk is ready to ask that. Like what happens to refresh in high bandwidth memory, especially when the high bandwidth memory is used so close to a GPU, for example, and it's very hot. It's good to understand that. Clearly, there are several promising directions. We talked a lot about the first two, which is eliminating unnecessary refreshes and enabling that works, reducing the refresh rate with online profiling and detecting and correcting errors. We didn't talk about this one. I'll just mention this one briefly, but you can also parallelize refreshes with accesses. This is along the lines that you mentioned, but while you're doing a refresh, you can also enable access to some other subarray, for example. And this is more finer grained refresh in the end. I'm going to talk about that a little bit more. Yeah, we already talked about this. Yeah, I think going into the future, certainly there's more work to be done, especially in understanding this phenomena, but also exploiting application behavior at the software end. How do you basically somehow make refresh not a problem, if you can? So there's a lot of room for new ideas, I think. Let me mention the refresh access parallelization. This is actually interesting. This doesn't get rid of refreshes. You do the same number of refreshes, but what this does is, while you're doing a refresh, you can earn access to some other subarray in DRAM. And that's what this paper proposes, and it shows good results. More recently, Giray, who's not here. Where's Giray? I'm used to Giray being here, and I'm picking on him, but he's been a TA for this for a long time. But basically, Giray and Ataberk also have shown that in real DRAM chips, you can do partially what this paper proposes. Basically, by violating the timing parameters in DRAM chips, you can activate another row in another subarray while you're activating one row in one subarray. That's the idea. So real DRAM chips are capable of this even without any modifications. This is actually really interesting that you can do this sort of stuff. So this is another direction that's very fascinating, I think. What can you do in DRAM chips that's not specified in their current behavior? You can take DRAM out and actually remove DRAM from there. What can you do in chips that's not specified in their behavior? That's actually a general interesting problem, I think. We've been clearly doing that with DRAM chips because we have the infrastructure to do that. But I think this is fascinating that you can do it in real DRAM chips. Okay, I will mention this paper again. Industry is writing papers about it too. And what we have talked about is actually, we've talked about refresh. So if you look at DRAM process scaling challenges outlined by Samsung and Intel, they talk about refresh, variable retention time. Add RowHammer to it. They couldn't talk about it, but add it over here. So two of them are related to refresh, as you can see. Write latency, we're going to talk about that in the next lecture. So I think what we have been talking about is really intelligent controllers also. This online profiling, you need to have a good controller and maybe DRAM support to do that. So this is an example of what we will do, hopefully, more and more in this course. Good ideas are interesting, but they may not be implementable. But making them work is really the tough contribution. I think ideally you would come up with a new good idea and also make it work. But it may take time to make it work. As you can see, it took us like at least 5 years to make some of these things work. And we still don't know exactly how to use the Bloom filters, for example, to make the exact proposal of Radar work, because you may need to remove some things from the Bloom filter to not lose a lot of the benefits. Okay, that brings me to the end over here. It's a great time to take a break, unless there's a burning question on refresh, because we're going to switch gears to latency. Okay, I don't hear anything. So let's take a longer break today, 15 minutes, and then we'll start latency. Nope. You have a new idea about refresh? You look like you do. Okay, let's get started. Well, that's right on time. Let's get started. Oh, I cannot see the, okay, it's here. It's okay on Zoom, right? You can hear. It's not? Okay. Okay, before we get started on latency, there was a comment one of your fellow students made about refresh and RowHammer. These are actually, it's interesting because these are two big scaling issues, technology scaling issues we have. And refresh is very fundamental, clearly. And ideally, you would like to get rid of refreshes, right? As much as possible, as we have discussed. But RowHammer introduces new refreshes. So there's a tension between these two scaling issues that are pulling us in different ways. That's a bit unfortunate because we don't want to solve RowHammer by increasing the refreshes, but that's what may be happening if you use the reactive refresh approach. And certainly you don't want to use the increased refresh rate across the board approach as we have discussed, right? That's similar to having ECC for every row, in my opinion. Yeah, but it's good to make this observation, I think, to see how you can solve these two big problems. Any thoughts? Otherwise, I'm going to switch gears and move to memory latency. Okay, let's move to memory latency then. You can of course have more ideas on refresh. So you may have seen this slide before. I don't know if Ron presented it, but these are 4 key directions that we're looking at in my group, and we've discussed actually a lot of it so far. Certainly, we discussed a lot of the memory-centric architectures, where the goal was really to not just be energy efficient, but also high performance. But energy efficiency is actually really important because we're wasting a lot of energy, as we discussed. So we've discussed that. We've discussed RowHammer, but there's more going on in security. But you can generalize this fundamentally secure, reliable, and safe architectures. I think that's really important. We discussed a bit in one lecture on architectures for genomics, for example. There's also architectures for other key applications that you have seen in some of the lectures, like graph analytics, for example, goes into that. But we have not discussed this part, low latency. And I think you can clearly, memory-centric architectures reduce latency, right? If you actually do the computation close to memory or right inside the memory cells, you're fundamentally reducing latency a little bit to do that computation because you're not going to memory for every access. Well, you're going to memory, but memory is much closer, or you're exploiting the properties of memory. But there are other ways of reducing latency. How do you design systems to be low latency? And predictability is something we're going to see. How do you design systems to be a higher quality of service is going to be important. So let's take a look at this part. But I think it's good to look at the slide and think, like, what else can we do in this area? This clearly covers a lot of ground, but it's good to always brainstorm what can you do in this area. I believe the last one is also very important, and we may discuss that later. But I think I motivate latency as solving the hardest problems, because if you want to solve difficult problems, you really need to design faster computers. And faster just doesn't mean scale up the throughput, have many, many computers. In many difficult problems, we're actually bound by latency. So remember the discussion we had on genomics, for example, right? Some people think that it's just a throughput problem, right? Meaning, what is a throughput problem? You have lots of genomes that are generated, you want to process them, and their results may be available after 5 days or 10 days, right? You don't care about the latency as much, you care about the throughput of the problem. But unfortunately, that's not the case in especially situations that are life critical, right? You want to really quickly figure out what's going on and how you would react to some drug, for example, if you're in a life critical situation. And there are studies, I think Mohammed mentioned, studies with critically ill infants, right? You really want to quickly figure out what you would like to administer. So there are cases where latency is extremely important, and you cannot ignore those cases. And I think thinking about a problem as throughput problem sometimes is very backward looking, in the sense that it just shows that maybe you're not thinking about the problem more broadly, in my opinion. Maybe there are cases where you can actually, new applications that you can think about where that problem is much more latency bound, right? For example, I would love to have a machine where I can analyze my genome and I can quickly get results, right? I don't want to wait for 5 days. I want to quickly figure out what's going on. And then make it, because you need to eventually make a lot of the problems that you are doing are sequential decision-making problems, right? You're doing sequential decisions. If you don't get that result early, the other decision will be delayed, especially if you're in a medical situation, right? So basically, not thinking about latency is causing a lot of these sequential decision-making problems to be much longer latency. And in the end, we may not be solving it. I think climate is another example. This picture is supposed to represent temperatures and climate. There, I think we need even faster latencies, and our computers are not very good at latencies. Anyway, I don't want to philosophize too much, but clearly we have a lot of problems, and I think these require fast computation. These are just pictorial representations, and maybe understanding the brain is also important, right? I think it's fascinating how fast this is. I'm going to give you some numbers. We may think it's slow, but it's actually not very slow. Like some tasks that computers do are extremely slow. And it's actually good to think about this thing, because there was a period where psychologists and neuropsychologists and people who thought that, who wanted to use computers as a way of understanding the brain. Unfortunately, that effort failed very badly, in the sense that existing computers are a terrible representation of what is going on here, as far as we understand what's going on here. Because existing computers are not really able to explain things like decision-making that happens over here, even using these artificial neural networks, etc. Which probably should enable us to question, are we really doing the right thing with artificial neural networks, etc. So like if you studied psychology in 1990s, etc., computing was a paradigm for understanding the brain. It's no longer the case. If you're studying psychology today, and if somebody is teaching you should probably challenge that very quickly. So that paradigm is gone. People thought computing was a good way of understanding the brain, but I think we don't know right now. Okay, let me actually philosophize a bit more. This hierarchy of needs, I like thinking about psychology, as you can see. We didn't show this picture maybe, but maybe Juan showed it, I don't know. This hierarchy of needs argues that we need to start with energy. Energy is the most important thing. Well, that's what Europe is thinking right now, especially. Energy is the most important thing, we'll see. Well, maybe not energy. Maybe it's really reliability and security. That's what Europe also is thinking today. But maybe Europe should be thinking this: how to react well and fast. I think this fits very well with my political analogy of what's going on in Europe today. Basically, these things are very interrelated. That's what my point is, right? If you don't have energy, do you really care about safety and security? Or if you don't have reliability and security, do you really care about whether you have energy? I think that's a tough thing. People have come up with the term energy security, right? How secure is your energy? I don't know. But I think basically we've covered energy, which is the energy efficient computing. We've covered safety and security. But if you have speed, maybe you don't care about whether you have energy because you would solve the problem with as low energy as possible and then you would move on, right? Of course, it's a joke, right? But I think there's some truth in every joke also. If you're fast enough to detect some things, if you're basically extremely quick at some things, maybe energy and security or other stuff doesn't matter because you would detect an attack much more quickly. I think that's where speed actually is also very fundamental. That's my philosophical perspective. I don't know if Maslow agrees, but we will never know. Okay, so that's what we're going to talk about: low latency and speed, essentially. But I will point you to this beautiful talk by Satya. I mentioned Satya in the last lecture. This is a nice talk that he delivered at SysTor a couple of years ago. It's online, you can find it. Well, it's over there. Basically, he's motivating latency from an edge computing perspective, saying that we're going to do a lot of stuff on the edge. So this is the cloud. There's other stuff that are close to us that look like a cloud, like the vehicle systems. But there are really other stuff that are at the edge in our hands, for example, very interacting with the environment. And in a lot of these cases, we need a lot of things, of course, energy efficiency as well, but latency as well. So, for example, the stuff that you're wearing on your like VR headsets, for example, AR, VR headsets, there are going to be a lot of latency is extremely important here, because if you don't react quickly enough, then you're not going to really be able to provide the environment where people will feel that something is real, right? You could argue that is that a good thing or a bad thing, but they're good applications clearly, right? Technology is agnostic to good or bad. There are good applications of this also. Okay, so that's one example. And if you look at his keynote, he mentions that there are a bunch of problems that need to be solved. Surprisingly, he doesn't talk about energy. I would add energy over here, but anyway, I think latency is a very important thing because you need to be highly responsive. And these are some numbers that he provides. I didn't verify them, but you can see how fast we are. For example, for VR head tracking to be good enough, you need a response time of 16 milliseconds. You can watch his lecture for exactly what it means. And he has some videos also. Essentially, he suggests that to be superhuman, we need to solve problems that are like better than humans. We need to beat these speeds, basically, because there's some additional processing time that's needed, and you still need to satisfy this, right? And you can see that face detection is also pretty bad. I don't know if that number is correct, but I could imagine. Yeah. And I think genome analysis is another example of this, although I don't have those numbers over here. And we discussed a huge memory bottleneck over there. Any questions so far? I'm still motivating. So okay, we talked about data-centric architectures in an earlier lecture, and we talked about processing data where it resides. But enabling low latency and low energy data access is actually a very important part of a data-centric architecture. If data is a very important resource, you should really access that very quickly, basically, and also with very low energy. And today's systems are actually not so good at doing that. I mean, as we discussed, there's a memory hierarchy that's built. You're doing it in your labs. But that memory hierarchy assumes some things like locality, right? Very good locality. In many applications today, we don't have that. So let's talk about that a little bit. So I'm going to talk about some fundamental trade-offs in latency first. First, let's take a look at some real data from the field. This is old, but actually I should have replaced it with Minesh's position paper. Altavak, you should remind me of that. Yeah, there's better data that we have that spans until 2021. Essentially, it's the same thing. This is about, I don't know, 18 years of DRAM. And we're looking at the improvement in capacity. The improvement, I'll give you that number, is 100x. And this is still going reasonably well. It's slowing down a little bit due to issues like RowHammer, etc. But capacity has improved over the course of 18 years by 128x in the most common technology, DDR technology. How much do you think bandwidth has improved? What does the curve look like? Quite similar? That's one suggestion. Any other thoughts? It's going to be 128x? Increasing, okay. Bandwidth is flat. Okay, that's an opposite thing. Okay. Any other thoughts? So it has improved, but not as much, basically. And bandwidth you can actually improve by adding more pins to the DRAM chips, by increasing the frequency. Usually what's happening today is you increase the frequency of the DRAM chips, which is very bad for energy also, if you think about it. Adding more pins is very costly, and also it may be bad for energy. Yeah, this is not an easy thing. Adding more chips and somehow accessing them in separate ways, it may improve bandwidth, but it may actually degrade latency. What about latency? Okay, yes. It gets worse, okay. Why would it get worse? Okay. Is that correct? He's not sure. So what latency is bad in DDR5? Oh, okay. I mean, it could be possible, yeah. I mean, yeah, some of these latency parameters are getting worse. You're right. I don't know if overload latency is getting worse. I'm not sure about that. I think we should look into it for sure, though. That's a good point. Any others? So basically, I think this is not looking at DDR5 clearly. This is stopping at 2017, but you can see that this is the row cycling latency also, TRC, a particular parameter. Basically, it's improved by only 30%, reduced by only 30%. So you can think about why is the reason. We're going to talk about the reasons, actually. One of the reasons is business reasons, because higher capacity chips sell, whereas this, it's not clear. At least the business model is not geared toward that. So there are some business reasons, of course, over here. We're going to question, is this a good idea? And is this fundamental? But basically, this is the fact. Memory latency remains constant. And as you mentioned, some of the parameters are actually getting worse. This is even old data before DDR5. You can see that some parameters like pre-charge latency is getting worse a little bit. Restoration latency is getting worse and then better. Yeah, this is real data from real DRAM chips. But we know that latency is critical for performance for many applications. I'm not going to harp on this again. I will mention this study where we showed that new DRAM types actually increase latency. So this is consistent with the DDR5 observation that you made earlier. We basically studied a bunch of real workloads and look at different effects of different DRAM chips. So this is actually not an easy study to do. It's a simulation-based study because you need to study workloads and different DRAM types. Ideally, you would make this on a real system, but unfortunately, there's no real system today that supports more than one type of DRAM. So you have all these different DRAM types that I'm going to show you in a little bit. Most of the time, when you design a memory controller, it supports one, maybe two, if you're lucky, DRAM standard. Why? Because these DRAM standards are completely different from each other. And especially the physical interface that you need to interface with the chips. This is a mixed signal circuit, mostly analog circuit, actually, that you need to design to communicate with the DRAM chips. And that needs to be operating at very high frequency. And the signaling is actually very different in different DRAM standards. And actually designing that physical interface such that it can operate with all possible DRAM chips, DRAM standards is very difficult. That's actually one of the main reasons why you cannot support many different DRAM standards today, because that physical interface is extremely costly. Costly in terms of money, as well as chip area, as well as design time. So it's costly in everything, basically. This is one of the hardest part of the circuits to design, actually, the memory controller. We're going to look at that in later lectures. So essentially, you cannot test different types of DRAM on a real system. So that's what we did, basically. In this study, we actually do a simulation-based study to understand how different workloads work with different DRAM types. And you can read the paper. These are different DRAM types we examined at the time. So now there are newer ones, like mentioned, DDR5. I don't know if you can buy them yet, but soon, hopefully. So let's take a look at the differences. I don't want to go into a lot of detail in terms of the details and DRAM types, but you can see that they make some different design decisions. The number of banks have increased from DDR3 to DDR4. DDR5 is graphics DDR, specifically designed for graphics. So it's supposed to be very high bandwidth. You can see that some of these introduced bank groups. Some of them increase latency because of the bank groups, because you need to switch between different bank groups. There's additional latency over there. Some of them increase area and power, like DDR5. And then there's a 3D stacked memory technologies like HBM. That's what the lecture is going to be about on Tuesday, 3.0, HBM3. That makes some other design decisions, like, yeah, you have a logic layer over here. And for example, hybrid memory cube makes a design decision of having narrower rows and higher latency as a result. And then there are other technologies like wide I/O, which was designed for low power systems. And then LPDDR3, LPDDR4. These are actually the DRAM chips that are employed in cell phones, for example, or new versions of laptops. So there are a lot of different types of DRAM that are designed today. Fundamentally, they're all vulnerable to what we have discussed earlier. So everything we discussed earlier applies. What's different here is the design decisions in terms of some things over here, as you can see, and also the interface. So the signaling that's used in low power chips, for example, is very different. It uses low power signaling in the interconnects. One of the reasons why it's low power is actually the main reason why it's low power is because of that, actually, not any other architectural decision. It's really the interface. And to be able to connect with those chips, you need to design a completely different memory controller. Okay, so the point from that paper is this. One point I would like to mention is this. Essentially, new DRAM types sometimes increase access latency in order to provide more banks or higher throughput. And this leads to reduced performance or not improved performance in the best case. So you can see, for example, here, this is, if you look at DDR4, the blue curve, the speed up that you obtain over DDR3 is essentially non-existent, even though you pay more for the DDR4 chip. Right? You get higher capacity, but the speed up you get is non-existent, let's say. Some other technologies like hybrid memory cube, in some cases you lose performance, right? There are some applications where you lose performance over here. So this paper analyzed that and reports that. And I think this was also reported by other works, but this is a more systematic study. So that's the idea. Is this a good thing to do, basically? It's good to question. Why are we not reducing latency? And is this a good thing to do for the performance of our systems? And if you want to actually take advantage of some of these technologies, you may need to rewrite your application, meaning your latency is not improving fundamentally, but your bandwidth is improving. That's true in many of these cases. Then you need to basically rewrite your application somehow to take advantage of the more bandwidth. That's the question. Some applications actually may not be able to make up the increased latency, even though there's additional bandwidth that's provided by the main memory. And you can see that that's happening with high bandwidth memory over here, as well as hybrid memory cube over here. You're losing performance because speed up is lower than 1. Okay, so there are other key takeaways in the paper that I will not go into a lot of detail, but you can read the paper. Bank parallelism is not fully utilized by a variety of the applications. Spatial locality is still important because many DRAM types actually take advantage of spatial locality with large row buffers, for example. Not all of them. And for some classes of applications, actually low power memory is very good. It provides significant energy savings without sacrificing a lot of performance. So I would recommend you take a look at that paper. And this is summarize things. And a lot of things in the paper are actually open source as well. Thoughts on this? Yes, please. Yeah. Hmm. Yeah. Well, optimizing for cache accesses is not necessarily optimizing for bank parallelism, actually, because when you optimize for cache access, you're trying to maximize your locality. And ideally, what you're trying to do over here is minimize the misses to the memory, right? But if you really want to take advantage of bank parallelism, you want to cluster the misses, such that whenever your misses occur, all of them occur in parallel, and hopefully they go to different banks. Right? So optimizing for locality doesn't take into account this at all. In fact, there are compiler transformations that were proposed like as early as micro 1999 that basically try to balance this. They give up a little bit of locality so that whenever you get misses are clustered. They happen together so that they happen in parallel in your banks. Does that make sense? Oh, okay. So that's a different question, basically, I think. Yeah, that's true also. Yeah. Yeah. So that's a great question, basically. Yeah, what happens basically when you get a cache miss? When you get 2 cache misses, for example, do they map to different banks, for example? Yeah, there are papers that are written on that, basically. So you need to ideally take that into account. Like when you get a cache miss, you would like to, for example, you're evicting something and you're bringing some other data from the same set. Existing processors use some randomization functions in the main memory controller so that these go to different banks. Because you don't want the last thing you want to do is what you're evicting goes to the same bank as what you're reading from, right? So existing processors actually have some randomization. We'll talk about that when we talk about memory controllers briefly. But the thing that I was mentioning is a different issue. If you actually optimize your software such that you get a high cache locality, that doesn't mean that your misses are clustered. Yeah, it's very interesting, actually. Optimizing the entire hierarchy is a very difficult problem. This is where maybe some interesting machine learning techniques can help. And that's why we've been looking at reinforcement learning in the memory hierarchy, but we have not been looking at this aspect. So there's an idea for you, Ataberk. And we can tell Rahul about it. I'm picking on Ataberk today. Maybe I should pick on someone else. Okay. Okay. Okay, Ataberk is actually working on some stuff related, right? Yeah. You can talk to him about that. Okay, so essentially, new DRAM types are not helping latency. Even if they may not be increasing all the time, they're not helping. But we know that latency is a significant limiter of system performance energy efficiency. In fact, I think it's always good to think about. I mean, there are folks who, as we mentioned earlier, claim that you can tolerate all latency with more bandwidth. I don't believe that really, because you need to really restructure your code to tolerate that latency. And the problem we have today is the latency are so high that to tolerate those latencies, you need to have a lot of bandwidth. And we're kind of stuck in this mindset because some people think latency is not as important. For example, if you talk to NVIDIA, they may tell, oh, we have so much parallelism in our code that we can tolerate all that bandwidth. And then you talk to them, oh, we need more bandwidth. Well, why do you need more bandwidth? Well, maybe your latencies are quite high, right? And that's actually true. The latencies are so high that they need more and more bandwidth to tolerate the problem. So they're in this vicious cycle, if you will. They don't realize the real problem, which I believe is latency. If you get rid of a lot of the latency, actually, the bandwidth need will also reduce, because a lot of the bandwidth need comes because of the queuing delays that you have. And maybe you can actually support more applications. So it's good to think about the interrelation between these things. Latency actually exacerbates a lot of things in the end. It exacerbates the bandwidth need and the quality of service problem, as we will talk about later. It also increases the processor design complexity. We've discussed this. I'm going to give you an example. This is actually a slide from my PhD proposal. I also use it in my defense. That's why it has the UTECE over here. This is circa 2003, I think, or something like that. Nothing has changed. It's all correct. Yeah, that's why that's the beauty of working in a fundamental area, right? 5 years later, your work doesn't become obsolete. It's going to hopefully stay forever. Well, that's a strong claim. Hopefully, I said. Okay, but basically, you can see that these are the conventional latency tolerance techniques that are employed today, right? Caching, prefetching, multi-threading, out-of-order execution. They're all employed in today's processors at many levels. Unfortunately, they may not work, as we discussed earlier. We're going to see prefetching later on in this course. We're going to talk about multi-threading a little bit, but not too much. You've seen out-of-order execution in digital design and computer architecture. How many people are familiar with out-of-order execution? How many people are not familiar? Okay, there are some people. So hopefully you read it up. Sorry, we don't have enough time to cover. But the idea here is to execute instructions out of their original program order so that you can tolerate some latency. Caching, prefetching, multi-threading. I'm assuming everyone's familiar with caching, prefetching, multi-threading. Who's not familiar with any of these? It's fine to say I'm not. Okay. Multi-threading also? Okay. These are techniques that are employed in real processors to tolerate latency. Caching, I'm not going to talk about it, but these techniques work with usually regular access patterns, although there's been advances in prefetching with irregular access patterns also. Multi-threading works well to tolerate latency. Basically, you have multiple threads and you're tolerating the latency of any single thread that way. But works if there are multiple threads. It doesn't work if there's a single thread that's really important. Out-of-order execution tolerates cache misses that cannot be prefetched, but it requires extensive hardware resources. All of these require extensive hardware resources, essentially. So this is essentially the perspective today, and we're going to see more of this. But if you look at this, any of these, none of these really reduce the latency. There's some memory latency out there. We're talking about memory latency, but you could also think about network latency, storage latency. None of these really reduce the latency. What they do is tolerate the latency or hide the latency from the processor's perspective. There's a program that's executing in the processor. If it hits in the cache, the latency is gone. But there was some latency to bring the data into the cache, right? In a sense, caching is still a latency hiding mechanism. True, it's reducing latency from the processor's perspective, but it's not really fundamentally getting rid of the latency. That's why we need more and more cache to tolerate the latency. That's why we need better prefetchers to tolerate the latency and more complicated things. So this is actually all complicating the memory hierarchy. I will mention since I mentioned that, how many people know about run-ahead execution here? That's good. This is a topic I like talking about. How many people don't know about this? It's okay to say that. Okay, so this was my PhD thesis. I will mention it over here because it's another technique that actually doesn't fundamentally reduce the latency. It's essentially a way of making out-of-order processors simpler. So ideally, you want perfect caches, right? You basically have all loads hit. That's great. Well, that's not necessarily great if you're thinking memory-centric perspective, right? Because there's something going on that brings the data into the perfect caches, right? This picture is a very compute-centric view of the world, if you think about it. So it's good to question these things. What makes those caches work? Okay, ignore that. Assuming that you make the caches work, this is great. If you have an out-of-order execution processor, what happens is you get a cache miss. Normally, caches are not perfect. And then the processor continues executing. After some point, its instruction window, buffers of instructions become full. So it cannot continue processing instructions. So it stops basically tolerating latency because it cannot fetch more instructions because it's too complicated to fetch more instructions, right? So it stalls for a long time. And the stall can be very long, hundreds of cycles. And people are trying to increase that latency even more, by the way. So if you think about DDR5, it's not bad. But people are trying to change the DRAM interface with something called Compute Express Link, for example. That enables you to have even bigger DRAM. But unfortunately, now you have to communicate more to get to it. So that increases the latency even more. We're not going to talk about that right now. I think there are some benefits to the idea, but it's not good for the latency direction, if you will. So, okay, but basically that's a stall. You wait for hundreds of cycles. And then the data comes back. That's where the miss gets serviced. And then you continue computation. Soon after, you get another cache miss. So in a memory-intensive workload, the execution looks like this. That's why most of the time you spent waiting and most of the energy you spent on data movements. So running the idea is very simple. You basically compute, and then you get a cache miss. After some point, this cache miss becomes the oldest instruction in the processor. So you checkpoint the architectural state of the processor so that you can go back to that state. And you go into a special mode. In this special mode, you don't stall. You basically continue executing instructions, but ignore the results that you don't have. So that load one miss, you don't have the result? Okay, ignore. Move on. Anything that's dependent on it, get it out of the window so that you don't do anything with it. But everything else that's independent of that load, you can execute. And there are a lot of things that are independent, hopefully, in your instructions stream. And hopefully, this enables you to get to the independent load early, and you start the cache miss. So you can see that we're parallelizing the cache misses over here. Hopefully, that goes to a different bank also. That's the hope, right? Always. So we're increasing memory level parallelism, and hopefully that memory level parallelism increase maps to different banks, so you increase bank level parallelism as well. So once the load one miss returns, you get out of this mode, you flush the pipeline, you restore the checkpointed architectural state, meaning you start from the same load that caused you to enter this speculative execution mode, and then you re-execute the load, and then you keep computing. And while you're doing that, there's the other miss that you started, load two miss, hopefully completes. And when you actually get to load two, it hits in the cache. And that way you save cycles. So that's the idea. This way, basically, what you're doing is you're using the stall cycles to do some speculative processing to enable parallelization of cache misses. Right? It's a beautiful idea. Out-of-order execution also does this, right? Here, basically, so this actually ties back to what we have discussed earlier also. Out-of-order execution can do this, assuming it has a long window, large window. It should be able to eventually get to this load two miss if you can process many, many instructions into the future. But to be able to build that window is a very difficult task. So run-ahead execution basically shortcuts saying that I have a small window, I'm just going to use it to speculatively execute instructions without requiring a large window, without stalling essentially. So this is an example latency tolerance technique. And this is a very compute-centric technique also. It's also employed. I mean, this improves performance. All of the other techniques improve performance also. This is data from Sunrock. Basically, these folks show that using run-ahead execution, they called it Scout. It's also an interesting name because you're scouting ahead in the program, right? Figuring out getting to these cache misses earlier. So these folks show that you get 40% better performance with a small cache size. And if you basically with a 1 megabyte cache size, you get the performance of an 8 megabyte cache. So you basically you can use this for improving the performance for a given cache size, or you can use this for getting the performance of a larger cache size. You can think of it that way without building that larger cache. And these are their workloads. And this is consistent with the results that we have reported earlier. So if you want to learn more about it, we're going to maybe cover this. I don't know. We're going to cover prefetching, but I don't know if you will cover run-ahead execution in this class. But you can read more about it. Any thoughts? I like talking about it because I think it's a very simple technique to talk about. But, and this is implemented in a real process. Actually, NVIDIA Denver is a, oh, you had a question? Okay. While you're doing that latency, I'm going to overlap the latency. NVIDIA Denver is one processor that implemented it. Actually, this is a very nice paper that NVIDIA wrote that talks about this work in their CPU, not in their GPU. Although they did consider in their GPU also. They don't talk much about what they implement in their GPUs. Yes?
When we are doing the run-ahead instruction.
I think that's not working.
So when we are doing the run-ahead instructions, how do we determine if they are conflicts with the data that is being tried to access in the memory?
What do you mean conflicts?
Because we can only do the instructions that do not depend on the on the data that we are trying.
Basically,
to
how do you determine which instruction doesn't have a correct value? Right. That's what you're asking.
No. How do we know if we can do an instruction in run-ahead or if we have to wait for the data?
Yeah. So basically, I didn't explain the full mechanism, but if you get a cache miss, you basically mark the data as invalid, saying that, for example, you're loading into register 2, and this got a cache miss. This load got a cache miss. You mark register 2 as invalid, and you basically any instruction that needs register 2 will source an invalid value, so you cannot execute it because the data value is not available. You just basically figure out what are those invalid instructions. This propagates to the out-of-order execution machinery in the machine. Any invalid instruction gets dropped, basically.
Is it done in hardware or in
It's all done in hardware. Yeah, this is all done in hardware.
So the instruction is put in the pipeline, but only when it goes to try to access the data in the register.
Exactly.
That doesn't work and it's dropped.
Exactly. Exactly. Yeah, it's propagated through the register file. Okay, now you went into more details on the mechanism, which is good. But there are other techniques also. I mean, you could also predict the value, right? You could basically say, I get a cache miss, I'm going to predict that it's 0, value 0. That's not a bad mechanism, actually. It works not so terribly, let's say. That way, you don't need to propagate these invalid bits. You basically say the value is 0. Any dependent instruction will be executed, assuming that value is 0. Yes, you'll get some garbage values, and it's not too bad in the end. Basically, you will not do, the key is you will not do anything wrong. Why? Because it's a purely speculative mode. You will never commit these results to the software. You'll never report these results to the software. It's pure speculation. It's like a branch prediction that you've done. Eventually, you will go back and re-execute everything. Yes? Mm-hmm. Yeah, I mean, you're talking about the details of Meltdown right now, which is something we want to not get into. But basically, you can implement it correctly. So they speculated too much. So they didn't do the permission check at the right place. So that led to the Meltdown vulnerability. Run ahead, basically, it doesn't change anything, essentially. This is, you see what I mean? Meltdown is easily fixable when you do the permission check at the right place. When you don't ignore something, basically. Yeah, but they don't do it due to run ahead. They just do it because they shouldn't do it. Yeah, Meltdown they shouldn't do. Spectre is much harder. Yeah, Spectre is much more fundamental, basically. We can talk about that later. Okay. Okay, so basically, none of these fundamentally reduce memory latency, including run-ahead execution, because run-ahead execution is actually a way of getting the benefits of out-of-order execution without building the machinery. So let's talk about really reducing the memory latency fundamentally. So basically, how do you reduce the memory latency? You should really reduce the latency in the device, basically. So these techniques are designed to tolerate the latency, but the device is still not the same latency, right? The device interconnects. Cache hierarchy, I think Rahul will have a lecture on cache hierarchy later on. There's a lot of latency in the cache hierarchy also, but there's a lot of latency overhead in the cache hierarchy also. So we should talk about that also perhaps later on. Because in order to get to DRAM today, you have to go through every single cache, right? And then the memory controller, and then the interconnect, and then the DRAM device. So there is a lot of latency in the hierarchy. And if you're, let's do this thought experiment. If all you're doing is random accesses, completely random, your caching is useless, right? But you're still paying the penalty of going through the cache hierarchy. And that could be like 70 cycles, 80 cycles. In some of these machines, it's going to be even more, right? If you remember the picture that Juan showed, AMD has a 96 megabyte cache. IBM Z series has some ridiculous amount of cache. What is it? Do you know? So I think it's close to 1 gigabyte, maybe more than 1 gigabyte. These are the Z series is designed for banking, like transaction processing applications. They're extremely expensive, but they have huge cache hierarchies actually. So going through that cache is actually, yeah, basically hundreds of cycles, even in the cache hierarchy like that. But let's talk about DRAM. We're going to talk about other latency issues as well. But I think what I'm just saying is really pointing out to the fact that modern systems are not, even though they're trying to use the caching, prefetching, etc., for latency purposes, in the end, these hurt latency, especially when they don't work. Right? If your caching doesn't work, you have to check the caches and then go to memory. Now you basically added more latency to going to memory. So the design decisions that are made are actually, in a sense, not that great from a fundamental latency perspective. Ideally, you would like to have minimal latency to access memory. Okay, so basically, let's talk about it from a DRAM perspective. Basically, modern DRAM is not designed for latency, as we have seen, right? The data shows that modern DRAM is designed for capacity and maybe a little bit bandwidth, but certainly not latency. And also, modern DRAM latency is determined by the worst case condition and worst case devices. So much of memory latency actually turns out to be unnecessary. So we're going to look at both of these aspects. So we're going to look at reducing the memory latency at the source of the problem, which is DRAM design. But you can apply a lot of these principles to other technologies also. And people have done that actually for emerging technologies. Flash memory also. It's good to think about that. I think everything that can be done in one technology, if you think hard enough, can be applied to another technology. But you need to think a little bit hard enough. My favorite example actually is, you learned about MBIT, right? Bulk bitwise operations in DRAM. While my PhD student, Vivek Seshadri, was developing that idea, MBIT, I told him there should be a way to do this in flash memory also. And 5 years later, Jisung and Rakesh and Mohammed over here figured out a way of doing that in flash memory efficiently. So you just need to figure out how to do it, I think, and maybe think a little bit differently. Okay, so let's talk about that. But I think for this, we need to understand, like if you want to truly reduce memory latency of a device, you need to understand what causes the latency. And these are two major reasons why we have a latency problem, I think, in many of our memory devices. One is the design of, in this particular case, DRAM is for maximizing, the goal is to maximize capacity or area, not to minimize latency, basically cost per bit or capacity per area. And the second thing, we'll talk about this first, but the second thing we'll also talk about is we have a one-size-fits-all approach to latency specification. We use the same latency value for every single temperature, DRAM chip, parts of a DRAM chip, supply voltage level, application data. Some applications may be able to tolerate some latency, tolerate some errors that may be caused when you reduce the latencies, for example. So it's good to rethink how we approach latency in our systems. And in this lecture, we're going to look at memory, but I think the problem is actually much bigger than just the memory device itself. It's really the system design. Did you figure out? 2 gigabytes, even bigger. Yeah, L4 cache. Per what? Per drawer. Okay, yeah, that's an L4 cache, as you can see, 2 gigabytes. That's a lot. Okay, so let's start with the first one. But before that, let's review the DRAM chip a little bit. You saw this a little bit in the processing in memory lectures, but I want to spend a little bit more time here relatively quickly. So this is a real DRAM chip, as you can see. And you can think, there are many goals here. Cost. This seems like a different set of slides. Yeah, I did change the slide. Is this an old slide? Really? Okay. No, I'm pretty sure I changed the slide. And the way I changed the slide, maybe other slides are also not there. I don't know. Can you check? Maybe there's a fast way, but this should go really here. If you want to truly order this. Yeah, this 8B. Yeah. And I will add density here because these are actually relatively slightly different concerns. Yeah. So these are, I hope I didn't change any of this slide. Am I correct? Or did I not send you all the slides, new slides? Okay, but yeah, and then we can switch. But basically, these are the goals in designing the DRAM chip. What happened? And I would put cost as a top thing. And this is slightly very much related to density, but not fully also, because there are some other design decisions that you make in the interface, for example, that affect cost, but not necessarily density. But they're very closely related. So usually these are the top concerns. Reliability, as we have seen, is a secondary concern. It's still a very important concern, but it's secondary. And here the ordering becomes a little bit weird. I think energy and power come before over here also, but anyway, I don't want to reorder them. But latency is usually a late concern, and maybe not a concern, right? Okay, so let's take a look at how the DRAM chip operates. Some of this is going to be reviewed, but if you look at this is a conceptual view of the DRAM bank over here, and we're just showing two different subarrays inside the DRAM bank. The real life is a little bit more complicated, of course. But you have a sense amplifier, essentially a row of sense amplifiers, and sense amplifier is a cross-coupled inverter. And the sense amplifier can be enabled or disabled. And you can see that this is how it's sensed. There are two stable states in the sense amplifier. Remember, digital design and computer architecture, it's a cross-coupled inverter, right? And it has stable states. If the sense amplifier is enabled, the top part can be VDD and the bottom part can be 0, or the other way around, the complement of it. And this is logical 1, it's sensing VDD on top, and this is logical 0, as you can see, because it's sensing 0 on top. Okay, so hopefully it's obvious. And the way sense amplifier operates it, assume that the voltage over here is slightly higher than the voltage over here, above some noise margin. When you enable the sense amplifier amplifies essentially the values, such that the larger value goes up to VDD and smaller value goes down to 0. That's the idea. And sense amplifier design is very interesting, but not so part of this course. Let's take a look at the capacitor. This is the capacitor's logical 0 state. It doesn't have any charge. Logical 1 state, it does have charge. Clearly, these are extremes, right? Normally, there's some noise margin. There's some empty state is some value, some voltage value that's below a noise margin, and fully charged state or logical 1 state is some value above a noise margin. Right? It doesn't have to be completely charged, but for illustration purposes, you can think of it that way. So capacitor is small; it cannot drive circuits, well, circuits meaning like an inverter. It has to be amplified basically, and reading destroys its state. So that's how you connect the capacitor to the sense amplifier. Basically, that's what we're going to look at. This is an empty cell. This is a full cell, and this is what happens when you connect the empty cell to the sense amplifier. It's 0, as you can see, and it should be sensed as 0 like this, and this should be sensed at VDD. Let's take a look at how that happens. Let's take the full cell first. Well, we're going to take only the full cell. Normally, this is the pre-charged state. You pre-charge the bit lines to half VDD, so that sense amplifiers, both sides are half VDD. And that requires some effort. And when you actually activate a row, you connect the access transistor, and now the capacitor shares charge with the bit line. It essentially perturbs the bit line, and this part becomes slightly larger than this part. And then you enable the sense amplifier. So that was activation. And then this DRAM circuit, there's a timed circuit internally that enables the sense amplifier after activation. And that basically starts the amplification process. And this part gets amplified to VDD, and this part gets amplified to 0. Make sense? Again, we're going through some abstraction levels over here. We're not looking at exactly what happens in the circuit equations, but you don't need that, I think, also to understand how this works. And then also the charge gets restored because this becomes VDD. Now this shares the charge back into the capacitor and fills the capacitor. That's how you refresh. That was what we saw was essentially a refresh also, right? Because you do not necessarily start with a fully charged cell. You started with a cell that's above a noise margin over here. Okay. Okay, and then you have you build a subarray out of this. So this is one cell, and then a sense amplifier and a bit line. You basically add more cells in the bit line, sharing the sense amplifier. We're going to look at that. That's one cause of the latency, essentially, because now your bit line is getting longer, and there's RC delay on your bit line. And then you basically add the rows also, essentially extend each cell to have a word line, extend each row such that there is one word line that controls all of the access transistors on that row. Here you have basically a DRAM that has, I don't know, 6 rows and 4 columns, right? Okay. I like these pictures. These are Vivek's pictures, by the way. Okay, and then you have a row decoder and then an array of sense amplifier. Clearly, this is not 4. In real chips, it's maybe 8 kilobits, for example. And then this is really the subarray. This is the same subarray. It's called open bitline architecture. I'm not going to go into those details. We'll see that actually in one of the works later on. But this is one way of building DRAM subarrays. There could be other ways of building DRAM subarrays by connecting the cell arrays in different places, but we're going to ignore that for now. And then you build the DRAM bank. Basically, you have multiple subarrays. Different subarrays have different decoders, but they share one global decoder over here, as we will. I don't think it's depicted. Well, it's kind of depicted over here, but not to that abstraction level. So the row address activates a row, and the column address selects which data comes out of the sense amplifiers. Let's take a look at that a little bit. And then the DRAM chip is actually the entire thing. The interface is very narrow, so you get only 8 bits from a DRAM chip, and this is mainly for cost purposes. So you can see that the array of sense amplifiers is 8 kilobits. Here you bring down 64 bits of data, and then you send out 8 bits of data. So it's like a funnel. Here you have read a lot of data. It sits in the sense amplifiers. You bring out a small portion of it, and then you read out an even smaller portion of it. Well, there are reasons for it. Okay, I'll get into it. The reason is you need to read a much longer, you need to span a much longer span of the chip. So having 8 kilo of these lines that are going down, first of all, occupies a lot of area, but it affects reliability also, because those lines need to be reliable all the way coming down. The reason DRAM manufacturers don't pull down all of the lines from all the columns is, and they get a subset of them, is because they cannot make the entire thing reliable, low latency, and low energy at the same time, because that's a very long interconnect essentially. So you're back to the interconnect delay. How do you get the data out of the sense amplifier to out here? Now this is a toy picture. You're imagining 2 subarrays over here. Imagine 128 subarrays over here, or 256, or 512. And each of them may be 1024. So it's actually a very long interconnect. Having a long line for every single 8 kilo bits is not good for performance, energy, and reliability, because long lines actually have interference as well. So they actually separate these things, and you get only 64 bits. Maybe Ataberk can also discuss this later in the future. Yeah, that's also true. Yes, I didn't mention that there are also layout issues, unfortunately, that affect you, that limit where you place the lines. Especially because you don't have a lot of metal layers. I don't want to get into those issues, but you're correct, absolutely. Because you don't have a lot of metal layers when you manufacture a DRAM chip, you don't have the ability to actually put a particular interconnect over some parts of a DRAM cell, let's say, when we stick to that abstraction layer. And as a result, you actually don't have a lot of freedom, first of all. But I think even if you had the freedom, it's not a great idea to actually do this because of reliability issues. There's a lot of crosstalk that happens in these long lines, and those long lines actually affect your energy significantly. So a lot of energy gets consumed actually on these bit lines. So what I showed you over here these are local bit lines. But there is also a global version of these bit lines that take the data out of the sense amplifiers that are not shown over here. Okay. Okay, so basically you funnel 8 kilobits to 64 bits, and then the output of the chip is actually 8 bits. Well, some chips actually have, I think, 16 bits, even 32 bits. But the reason why this is small is completely because of a different reason, still related to cost. Well, we didn't mention cost, actually. If you have 8 kilobits of many of these, you actually have cost also. But here, there's a bigger impact on cost because now you're going off chip. Once you go off chip, you need to have I/O pads, input-output pads over here, and they occupy a lot of space because you need to communicate with an off-chip interconnect that's going to be high bandwidth, and that actually consumes a lot of area. And that's that determines a lot of your cost also. So that's why DRAM chips are actually very, even though internally they have a lot of bandwidth, externally they have very little bandwidth comparatively because of the cost reasons, cost considerations. Does that make sense? Like if you think about the processor chip also today has about 1,000 pins, let's say. A good fraction of it is dedicated to communicating with DRAM, actually. You could ask, why don't we add more pins so that we can have higher bandwidth to DRAM? And the answer is, you're limited by cost as well as area. If you want to add more pins over here to the processor chip, you need to add essentially more area, and you need to add more cost. Today, actually, I think a lot of the pins are used. It's very difficult to add pins to an existing CPU unless you increase the area even more. Do you agree? Okay. DRAM, I think, is a different issue. Here, there are a lot of other pins. We're not showing, there's power, for example, that you need to supply. There's voltage, etc. I believe you can add more data pins, but again, it's increased your cost. And also it increased your power. I should say that. Okay. Okay, I spent more time than expected over here, but I think hopefully these are clear. If you have questions, please ask. Okay, there's a shared internal bus between the banks. This was mentioned in row clone, if you remember the row clone earlier. And we know about the DRAM operation. I'll go through this quickly. You first activate a row that you want to get data out from. Assuming that you're interested in this data over here, you first activate the row that contains the data, which brings data into sense amplifiers. And then you send a read or write command to the column. The column address goes and you get the data out, hopefully. And then you need to pre-charge the array so that this row is closed. And then you can access some other row in the entire bank. Now these subarrays look decoupled. We're going to talk about that. They're not completely independent in existing DRAM chips because making them completely independent essentially makes them different banks. So which requires separate row decoders, separate bank IOs, essentially separate everything. So they're coupled because they share bit lines, for example, and they share a global row decoder that's not perfectly shown over here. But we're going to talk about that. So if you're interested in the DRAM background, I like the section 2 of this paper. It provides a good DRAM background. It doesn't discuss everything, but I'd recommend looking at that. So with that background, let's take a look at some of the causes of long DRAM latency. Any questions? Yes, please. Oh, pre-charging is basically setting the voltage level on the bit line to VDD over 2, so that you can do another access. So it does 2 operations. It's at a different abstraction level, but when you sense the row over here, sense the data, the bit lines are set to the values of each cell, right? And the row sense amplifiers have that value. If you want to read some other row, you need to set the subarray and the sense amplifiers to a state where you can read some other row. And what is that state? In that state, there should be nothing in the sense amplifiers, and all of the bit lines should be the reference voltage, which is VDD over 2. Pre-charge achieves both of those. Nothing in the sense amplifiers, disables the sense amplifiers, and then sets the bit lines to VDD over 2. Well, pre-charge is, let's say, part of a refresh operation. If you do activate and pre-charge, you're essentially refreshing the row and closing the row. Yeah. Okay. Anything else? Okay, so let's talk about some issues in the DRAM architecture design. This gets very interesting, I think. We're going to talk about one idea that tries to achieve a good trade-off. So what causes the long latency? what we have shown you is bit lines, right? We're going to look at those bit lines. So if you basically what I've shown you is you have cell array divided into subarrays in the bank. You have some subarray latency and you have some IO latency. And usually subarray access latency can be dominant. You can hide the IO latency a lot actually by doing some prefetching, etc. We're not going to talk about that. So there's some internal prefetching that happens in DM also. So you see that even DM has some prefetching mechanism certainly, right? Not as sophisticated as CPUs. It's just a longer line prefetching, let's say next few columns prefetching. Let's call it that way. So why is the subarray so slow? Essentially, this is the depiction of the subarray, and the sense amplifier needs to be large so that it can sense the values in the cell. It actually is very large in today's systems. To amortize the cost of the sense amplifier, you need to actually have many cells connected to the bit line, 512, 1024. If you do this amortizes the sense amplifier cost, right? I mean, one way of designing DRAM would be for every row, you have a row of sense amplifiers. Essentially, your subarray size is one row. That's extremely expensive because the sense amplifier is huge, right? You could do that. There's nothing that prevents you from doing that except for cost and overhead. But what people do is they design DRAM chips such that many cells are connected to a costly sense amplifier to amortize the cost. This is good because the overhead of the sense amplifier is small. Because if you think about it, sense amplifier is not storage. Storage is these cells. Sense amplifier is there to access the cell, right? It's really the access circuitry. You don't want to spend a lot of area on it. And if your mindset is, I want to maximize my capacity per area, meaning bits per square millimeter, you really want to have many cells and as few as possible sense amplifiers. So essentially connecting many cells to the sense amplifier leads to large bit line capacitance because there are many, many things connected to this bit line. As a result, it also leads to high latency as well as high power. Because whenever you're accessing this set of cells, you're perturbing everything over here, and there's a lot of capacitance and there's a lot of power that happens. That's true for the word line actually also, and maybe you can talk to Ataberk about that. The word line also is like that, right? You're accessing a lot of things on the word line. But let's not talk about that right now. Let's talk about the bit lines. Okay, so there's a trade-off clearly. What I just said is a trade-off. You can have a long bit line that looks like this, a single sense amplifier, many, many cells connected to it. You can make this faster by chopping it up and adding more sense amplifiers. But you can see that the area increased right now, right? Even by just looking at this picture, this is more costly. So you can make this smaller by doing this trade-off. So there's a very fundamental trade-off in essentially all memories that look like this. Area versus latency trade-off. And let's take a look at this trade-off. This is real simulation results, SPICE simulation results with latency. And you can see the latency over here and the normalized DRAM area. Ideally, you would like to be here, right? Cheaper and faster. That would be nice, but commodity DRAM actually is here. Basically slow and cheap. Because it has many cells per bit line. Now, by changing the number of cells per bit line, you can see how this curve goes. You can make the latency a lot smaller, for example, over here, and area a little bit larger. Now, area a little bit larger is actually pretty costly still. And there's some fancy DRAM that you can buy today by paying a lot of money that has this reduced latency. They essentially have short bit lines, and their latency is lower, as you can see. This, for example, RL reduced latency DRAM from Micron is one example. Fast cycling DRAM is another example. I don't know how much they still sell these things, but some people who really care about latency buy it. For example, very high speed networking routers. These use very fancy DRAM like this, so they pay a lot of money for this purpose. I think more people should pay money so that they produce more of these things, but not necessarily that, I would argue. So you can see the trade-off over here, right? Our goal is actually really get to somewhere here, ideally. But I think this is a very tough trade-off to break. If you figure out how to make all of your cells over here, you've either invented something really amazing or you're doing something wrong. Your calculations probably. More likely the other one. But you may have invented something also. So it's good to think about it. So we're going to try to achieve that. So we're going to try to approximate the best of both worlds. Ideally, we would like the small area but not the high latency. Basically, ideally, we would like the small area of the long bit line architecture and low latency of the short bit line architecture. How do we get there? Well, we're going to make a trade-off. We'll start with a small area that looks like this, long bit line. That's good. We're going to preserve that. But we're going to create a low latency area inside this long bit line architecture that looks like short bit lines. So how do you make that happen? Well, we're going to add isolation transistors over here so that we can isolate. So this portion of the subarray will be fast only if it's isolated from the other portion. That's the idea. So there's connections here that are configurable called isolation transistors. Oh, I don't know what happened. Sorry. Okay, I think, yeah, there are connections over here that are configurable called isolation transistors. When you connect them, you get the high capacity. When you disconnect them, you get the low latency. That's the idea. Well, you always have the high capacity over there, but you can access the stuff with high capacity when you connect them, right? Okay, that's the idea, with some area cost, of course. So this is called tiered latency DRAM. You get small area using long bit lines, and you get low latency using that little portion that looks like short bit lines when you isolate them. And isolation means you basically disconnect transistors over here so that the capacitance that you see in the sense amplifiers is low, right? Because the bit lines look short to the capacitor over here, to the sense amplifier over here. And according to the results in the paper, you get this is called the near segment. This is called the far segment in a subarray. The near segment latency reduces by 56%, assuming you have 32 rows over here and 480 rows in the far segment. But unfortunately, far segment latency now increases. Why does it increase? Anybody? Whenever you're accessing cells over here, your latency is higher than it would be in this architecture. Yes. Exactly. Yeah, those switches, these isolation transistors add additional resistance. Right? That resistance doesn't exist over here, basically. And that resistance apparently is quite costly. So there's always a trade-off. By the way, there's a bug over here. This should be below, or this should be at a 44% point. I don't know if anybody captured that. That could be a good exam question. What's the bug in this? I'm just kidding. Yeah. It tests attention. Okay, so DRAM power also reduces actually. Near segment power is, yes. Go ahead. No, you need just isolation transistor because it's the same bit line, right? It's the same bit line that's connected. Is it just connected to the top part or not connected to the top part? That's the only difference. I don't get that one. Yeah, let's discuss it because the only additional thing you need is to have the control over here. Essentially, another word line like thing that connects the isolation transistor. That adds latency also, yes. Okay, but we can discuss that later. Okay, so power also reduces because near segment, when you connect it, essentially the bit line is shorter. Shorter bit lines are also good for power, but far segment power increases, as you can see. And these are simulation results. And the area over it is actually about 3% due to the isolation transistors. So where does this take us? Let's take a look at the trade-off now. So ideally, we want it to be here, right? And near segment with 32 rows in the near segment gets us here. So that looks nice. But that's not the full story because far segment puts us back. So now you have something that you need to manage. So this is an example of heterogeneous latency memory. So it's really a substrate that can be leveraged by the hardware and software. There are many potential uses. The paper examines some of them. Essentially, you could use the near segment as a hardware managed cache. It could be an inclusive cache or an exclusive cache to the far segment. Basically, the question is, does a copy of the row that you cache in the near segment exist in the far segment also? Or do you swap things when you actually do the caching in the near segment? You could actually do the mapping in software. The operating system can decide what pages get mapped to the near segment or the far segment. Or you could simply replace DRAM with tiered latency DRAM and hope that it nicely works. But normally it doesn't work because it's a trade-off, right? You really need to have things that you more frequently access in this near segment so that you can take advantage of the low latency, because the other part is higher latency now. Okay, so the paper discusses a bunch of things. Let me give you an example. So if you have an hardware managed cache, essentially you're thinking of the subarray as this. There's a sense amplifier, there's a near segment, there's a far segment. And far segment is main memory, near segment is cache, and sense amplifier is some other cache that has to be there, right? So the question now becomes, how do you migrate a row between segments? And the second question is, how do you efficiently manage the cache? You've actually seen the first one. You remember the idea of row clone? Essentially, row clone was first kind of developed for this purpose, although it's really concurrent work, because row clone was rejected from an earlier conference, let's say. Let's put it that way. But basically, if you want to migrate a row, you don't want to do it the naive way. You don't want to go through the memory controller clearly, right? That's a very bad idea, as we have seen many times. You want to copy the source row to the destination row. And the idea is very similar to row cloning. You activate the source row first, which brings the data into the sense amplifiers, while keeping the isolation transistors on, of course, right? That's how we get the far segment row. And then you activate the destination row, which brings the data from the sense amplifiers to the destination row. And to make this faster, you can actually close the isolation transistors if you want. But there's a trade-off over there, which I'm not going to go into. So basically, this is actually quite fast, just like row clone. How do you efficiently manage the cache? I'm not going to talk about it. This is actually an interesting issue. I wish there was more work in this area, because this is actually a separate type of cache. So you can think of the processor cache, right? Processor cache is designed for the processor. But this is really a cache that's designed for DRAM. It's an in-DRAM cache. And its goal is not to serve the processor. Its goal in the end is to serve the processor in a compute-centric system, yes. But the way its design decisions are dictated partly by the structure of the DRAM, right? So it's a different way of thinking about caching. And why would it work? Because your cache lines are as big as your rows here, right? You're caching rows essentially. In a processor cache, you're caching cache blocks, 64 bytes. So that's why this may work. And you may get bank conflicts, and caching rows may help switching between bank conflicts. We will see that in a later, next week's lecture, actually. So the paper discusses some methods. It's actually not a great method, I think. So it uses least recently used replacement policy in this cache. I don't believe that's a great choice so far away from the processor. You need to really think about the locality characteristics of what's going on in the data that you're caching over there. And we didn't do that because our goal was not to really optimize the cache in the best possible way. As I mentioned last time, you can only do so much in a paper. Your goal is not to solve all problems in the world. Your goal is to demonstrate that an idea works and that idea could be useful. And later work can hopefully potentially demonstrate the caching benefits. And we will see some later work later. So even if you do, let's say, not so optimal thing, you still get performance improvement, as you can see. You get about 10 to 11% performance improvement averaged across many applications. You can read the paper for more detail, which is not bad. I believe it could be better. And you actually get good power reduction in DRAM, about 20%, as you can see. It's also not bad. So let's take a look at the one trade-off over here. We're going to end soon, but near segment length. Basically, this is how many rows do you have in the near segment. Even with one row, you get significant performance improvement, as you can see. This is actually interesting, right? Even one row of caching over there helps you because of bank conflicts, actually. You get a lot of bank conflicts, and caching, having the ability to cache one row helps you over here. The highest benefit is at 32 rows. But there's a trade-off. You get larger capacity as you go from left to right, but you also get higher cache access latency. Near segment access latency increases as you add more rows. And here we're assuming that you have a total of 512 rows in the subarray. Okay, so that's the maximum. Okay, I think that I timed it really well, as you can see. That was my goal to cover here until here. So that's the idea, basically. We're going to see more ideas on the microarchitecture, and then we're going to move on to how to actually get rid of some of the latency without even changing the architecture. But that's next week. Any questions? Any burning questions? Yes, please. So the latency is related to bitline length. How long is your bitline? Yes. Not only, I wouldn't say only. That's a big portion of the latency, but not the only portion of the latency. But this is a big portion. I think by thinking about this in all parts of the DRAM chip plus everything else, I think you can actually reduce a lot of the latency components. This is just looking at the bitline. Yes. Oh, data retention. That's a good question since we covered data retention. So there's no okay. There's no reason to think that it would be affected. We didn't do the studies, of course, because we don't have the real chip, but I don't think there is any reason to think that the data retention of the cells will be affected because you're not really changing something fundamental to the way you're doing refresh or you're constructing the cells. That's right. But you're doing that, those connections should not really affect your cell. I mean, it's true that there may be some second order, maybe third order effects that are very hard to determine. But at the first order, those connections should not really affect the charge inside the cells. You can think of this as also like when you're activating any row in the cell, you're doing some perturbation that affects every other cell, right? So that's true. Isolation transistors also are activating another row. I think Atarak agrees. Yeah. Yeah, that's a different question. Basically, you can potentially hammer things, yeah. But I'm not sure if it's going to be as like different from the RowHammer effect that we have today. So I don't think there is any reason to believe that the retention of the cells will be affected. I'm not sure hammering will be affected either. Maybe you can think about it. Because in the end, I would think about this to connecting the isolation transistor just like another activation. And to a first order, that's true. Okay, any other questions? Okay, well, you have a question? Okay, go ahead. Well, you should read the paper. Actually, you should have read the paper, but yeah. I think this we propose a change to the interface, basically. There's another command that you need to send to do this connection. But I mean, if you don't want to change the interface, you cannot do a whole lot, I think. Yeah. You could hide it, I believe. But I think it's not a clean solution, let's say. Is that a question or? Okay. When you switch between far segment to small near segment, the latency. Oh, okay. I mean, there is some latency because you need to deactivate, right? The isolation transistor. So there is some additional latency, yes. Okay. Now he's going to design the much more lower latency DRAM next week. Okay. So I'll see you next week. Have a good weekend. Uh-huh.
You don't care actually, even if